world-class RCC design engineers who participated in the writing of this bulletin under the leadership of Dr. Quentin Shaw from South Africa. Sunil, our understanding is that the presentations now will be run by the moderator, and that we will be available to answer questions. Is that right? Okay. So go ahead and start the presentations, please.
Good morning, and others, faculty.
Okay, Sunil, you should have the first presentation from Marco Conrad. Sunil, would you like me to run the presentation? Quentin, what do you think? Should I just start? Oh, there we go. Okay.
Good.
Good morning. Good morning, Mr. Harvey and Mr. Brett.
I'm not hearing any audio.
So, good morning, Mr. Harvey. Yes, ready to go. And on behalf of organizer, Indian Committee on Large Land, we welcome all the speakers for this session. And now I request you to start.
Quentin, are you hearing anything?
No. It's running, Mr. Sunil. It's running, but there is no sound coming through us.
Sunil, this is Michael. Can you hear me? Is the conference organizing online here? Sunil, we need to restart the program. We were not hearing the audio.
Okay, sir. Okay.
$2000s. Just recently, Icold has published the new bulletin number 177 on roller compacted concrete dams. I would like to use this opportunity today to thank again the lead author, Dr. Quentin Shaw from South Africa, and also thank all the primary chapter authors, Rafael Ibanez de Aldecoa, Timothy Dolan, Chongjiang Du, Francisco Ortega, Michael Rogers, Quentin Shaw, and Yao Zhu. Special thanks also go to Francois Couturier from Canada, who pulled together the French translation for this bulletin in no time, so that this bulletin could be published by Icold already now. This new bulletin was prepared to update the previous Icold bulletin number 126, which presented the state of the art of roller compacted concrete dams as at the early 2000s. During the intervening 15 years or so, the technology of RCC for dams has continued to develop, and the new document now presents the state-of-the-art technology as at 2018. This current RCC state-of-the-art will be outlined in this workshop and the presentations offered today. I understand there will be a break at about half time, and important would be the discussions and Q&A at the end, which will be live with most of the presenters being available live in this Q&A session. On behalf of all the presenters and also on behalf of the Icold Technical Committee on Concrete Dams, I would like to thank you for your interest in this workshop, and I wish you a fruitful event. Thank you very much.
Yes, please play the video PowerPoint from Dr. Malcolm Dunstan.
Good morning, ladies and gentlemen. I'll talk about world trends in RCC dams. There are now approximately 1,000 RCC dams that are either complete or under construction around the world, and therefore there is a significant amount of data. I will first talk about an RCC dam database, and then look at the distribution of RCC dams around the world, the design philosophies of RCC dams, the cementitious materials that have been used in RCC dams, the highest, the largest, and the fastest RCC dams. Then I'll look at the advantages of the speed of construction of RCC dams, and finally draw some conclusions. First, the RCC dam database. We've been maintaining an RCC dam database for some 25 years, and it is available for searching on our website, which is very simple to remember, www.rccdams.com. You can look at all the RCC dams in various formats. The simplest one is in tabular form. You can search for countries or the whole world or dams of different heights or containing different materials. You can also look at all the RCC dams in the country, and these are the 3 RCC dam projects in China, in India at the present moment. 2 in Maharashtra and 1 Tista in the northeast. Looking at Maharashtra, there are 2 projects, but there are in fact 4 RCC dams, Middle Vatana and the Gatgar project. Gatgar project in fact has 3 RCC dams, one of them is less than 15 meters high, so it's not shown on the database or the map view here. We have the upper dam holding the upper reservoir and the lower dam with the lower reservoir for a pump storage scheme. This is a photograph of the completed lower Gatgar dam, which is 100% RCC. The faces are GEVR, grout enriched vibratable RCC, and there is no seepage whatsoever. Now let's look at the distribution of RCC dams. This is the number of 15-meter plus high RCC dams completed each year. During the early half of the 1980s, there was a sort of experimental period, and there was a very rapid growth for 10 years, up to the mid-1990s, and about 10 years or a bit less of consolidation, shall we say, and then another rapid growth. This drop-off on here, in fact, in my view, is probably lack of reporting of the dams which have been constructed or completed. And I believe at the moment we're having somewhere between 40 and 45 RCC dams completed each year. Now, some countries do not report RCC dams or any dams less than 30 meters high. So I've looked at the situation with 30-meter dams. It looks pretty similar, slightly less. And this is a comparison between the two. You can see the shapes are very similar. This is the distribution of all 30-meter plus high RCC dams around the world. As can be seen here, that Asia has by far the greatest number, and if you put Asia and South America together, they take up just under 75% of all the RCC dams are in those 2 continents, and the other quarter is taken up with Africa, North America, Europe, and then South Asia, Middle East, and Oceania. Let us now look at the design philosophies used for RCC dams. There are essentially 5 different design philosophies. There's the hard fill dam. This essentially is an RCC dam which has symmetrical upstream and downstream faces and has a relatively low cementitious content. Then we have the low cementitious RCC dam. That's an RCC dam with a near gravity section which has a total cementitious content, that is Portland cement plus SCM, supplementary cementitious material, less than 100 kilograms per cubic meter. We then have the RCD dam, which is unique to Japan. The medium cementitious RCC dam, which has total cementitious content between 100 and 150. And then the high cementitious RCC dam, which has total cementitious content more than 150. In the database, just under 18%. We do not know what the cementitious content is, but if we take that out, we find that about 60% of all RCC dams are high cementitious RCC, and then about 7.5% are hard-filled, low cementitious and RCD, and around about 15% medium cementitious. But this is in terms of numbers. What in fact we should look at is what is it in terms of the volume placed. And if you look at the volume placed, roughly 2/3 of all RCC placed to date in RCC dams is high cementitious RCC. Hard-fill dams, roughly slightly more volume than numbers. But these three are all rather less, which shows that the smaller dams are built like this, the larger dams are built in here. If we look at the cementitious materials used in RCC dams, or in particular the supplementary cementitious material, are roughly about half of the ones we know are Class F, that is low lime fly ash. A few high lime fly ash. 2.5% is GGBFS, ground granulated blast furnace and slag. Then we have a combination of SCMs without any Portland cement, manufactured pozzolan. Well, these are all relatively low contents. Natural pozzolan here, which is growing, it's 12.5%, and no SCM, in other words, just Portland cement. Again, we have some unknowns, but if we take out the unknowns, again, we find roughly 2/3 Class F fly ash. So we have roughly 2/3 of all RCC dams are high cementitious content RCC, and roughly 2/3 contain low lime fly ash. This is the area which is growing natural pozzolans. Let us now look at the highest, the largest, and the fastest RCC dams. The first table shows the highest RCC dams, and the highest RCC dam in the world is Gibi 3 in Ethiopia, which is 246 meters high. And to be in the top 10, you need a height more than 165. Notice on the right here that of those 10, 8 contain low lime fly ash, 1 contains no SCM, and 1 contains ground granulated blast furnace slag. Of these 10 dams, 7 are in Asia. This is a photograph of Gibi 3 in Ethiopia. During impounding, the water level was about 10 meters below top water level when this photograph was taken. This is a table which contains the 10 RCC dams with the greatest volumes of RCC. And in order to get into this top 10, you need to have a volume of roughly 2.5 million or more. And the greatest volume is 6.5 million. In this particular case, we have 8 of the top 10 are in Asia. This is a photograph of Guanyangyang Dam in China, which has 6.5 million cubic meters of RCC. This is the table of the 10 RCC dams with the highest average rates of placement in terms of the average monthly placement of RCC. The fastest is Longtan in China, has an average rate of placement of about 143,000. To get into the top 10, you need an average rate of placement in excess of 85,000 cubic meters a month. And it is rather disappointing that only 7 RCC dams in the world completed to date have had an average rate of placement in excess of 100,000 cubic meters a month. Rather differently, in this table, 5 of these dams are in Asia and 5 are outside of Asia. This is a particularly interesting figure. At Longtan, in 1 month, 400,000 cubic meters of RCC was placed. And the peak days which have been achieved to date are a little bit under 20,000 cubic meters in 1 day. This is a photograph of the completed stage 1 of Longtan. Longtan is planned to be constructed in 2 stages. Stage 1's 192 meters high and stage 2 is 217 meters high. The RCC in this dam was completed around about 3.5 months early, and in those 3.5 months, over $500 million worth of power was generated. Let us now look at the advantages of the speed of construction of RCC dams. We'll look at 2 different projects. The first one is the Gatgar pump storage scheme in India. And the second one, in fact, are 2 projects, Sonla and Lai Chau, both on the same river, the Black River, in Vietnam. Gatgar pump storage scheme. This is a photograph of Gatgar, the lower Gatgar Dam, under construction, and it shows spit level construction. The dam was built in 2 halves which alternated. You placed RCC on the left abutment here and reached a certain level, and then moved over and placed RCC in the right abutment half. The big advantage of this is that by only placing in half the dam, you can place at least 2 layers per day, and therefore the RCC is always fresh on fresh. The other big advantage is during the placement of the RCC on the left half here, you can see the formwork for the galleries is being erected on the right half, and therefore the galleries do not actually impact on the average rate of placement. This is a photograph of the main gallery in the lower Gatgar Dam, some 7 years after completion. The walls of the galleries were formed of GVR, and the water is on this side. You notice that the galleries have had to be painted, and they've had to be painted to suppress the dust. These galleries are absolutely bone dry. There is no seepage whatsoever through the 100% RCC dam. This is a photograph of the downstream face when it's full, and you can see here on the downstream face there is no seepage at all. This is the quote from a paper presented by Mr. Icold and Mr. Joshi. Mr. Icold is the chief engineer, or was the chief engineer, of GOMID, the Government of Maharashtra Irrigation Department. Mr. Joshi was the chief designer. They produced a paper, The Success Story of Gatgar RCC Dams. Due to selection of RCC dam construction in lieu of conventional concrete or masonry dams, the project has benefited by 3 years of early commissioning and thereby the generation of 1,350 million units, the cost of which is 5.2 billion Indian rupees. This is equal to about half the cost of the project, not the dam, the project. This clearly tells a success story of RCC dams and its role in hydroelectric projects. Let us now look at Son La and Lai Chau in Vietnam. Son La in total contains about 5 million cubic meters of concrete, and this is a photograph of the RCC placement. Notice here there are footprints in the surface of the RCC, as there should be. Compare that with the surface of the RCC shown in the latest Icold bulletin number 177 and what an RCC should look like after compaction. Again, you can see the footprints. This is a photograph of the completed Son La project, the 2,400 megawatts. In the background is a spillway, which is the determining factor because the design inflow flood is 60,000 cubics. This is a press release by EVN, that is the owner of Son La, giving general assessment of Son La HPP. The government highly appreciates all ministries, etc. The Son La HPP has been accepted and taken over and put into operation 3 years prior to the approved schedule, and up to now it is operated effectively and safely. The RCC dam was in fact completed 1 year ahead of schedule. By the end of September 2018, Son La HPP has supplied 64 billion kilowatt hours, and it has contributed to the state budget something in the order of 11,000 billion Vietnamese dong, which is equivalent to $460 million. Son La had another project just upstream, a dam called Lai Chau, and Son La was so successful the Prime Minister of Vietnam awarded all the contracts for the construction and design of Lai Chau to the people who had been involved with Son La. This is a photograph of Lai Chau under construction. This is the completed Lai Chau project. Lai Chau was also completed a year early. And this is the press release by EVN. And in this particular case, the total contributory value to the national budget is more than 2.36 thousand billion Vietnamese dong. That's a value of 102 million US dollars. And let me draw a few conclusions. The original concept of RCC dams was to provide a simple method of construction with RCC spread horizontally from one abutment to the other. This would lead and has led to rapid construction. Unfortunately, some of this simplicity is being lost with sub-modern RCC dams, and the majority of RCC dams are not being constructed as rapidly as they could and should be. An holistic view needs to be taken during the design and construction of RCC dams, as every aspect of the design and construction impacts on other aspects. It is counterproductive to concentrate on any particular aspect, for example, aggregate production, and try to find the minimum cost solution, as it will almost certainly lead to a more expensive and probably slower overall project. Investment spent up front on the investigation of the design and construction of an RCC dam will always lead to economic benefits. For example, A very detailed study of the available materials and an extensive trial mix program for the Moachi Dam in Kenya led to the development of an RCC with a Portland cement content of 35 kilograms per cubic meter and the fly ash content of 185. This was probably the most economic and most contractor-friendly RCC dam ever achieved. Whenever you try to design or construct an RCC dam, there should be one thing centered to everything you do. Keep it simple, because with simplicity will come speed of construction, and with speed of construction will become quality and economy. Simplicity is the ultimate sophistication. Leonardo da Vinci, probably one of the greatest engineers who ever lived. Thank you.
So the structure of my presentation will be as follows. I will start off with talking about the purpose of the new bulletin. I'll then move on to talk about key new developments in RCC technology. And finally, I will look at the design of RCC dams, which is essentially chapter 2 of the bulletin. To start with looking at the purpose of the bulletin, RCC in dam engineering has now a history of more than 35 years, and despite having evolved to a level of some maturity over that period, developments in the technology are continuing. The first Icold bulletin on RCC was published in 1989, Bulletin 75, and this bulletin really recognized the early history of the technology and particularly focused on experience in the USA and Japan. A second RCC dams bulletin was initiated in around 1993 and took 10 years to be published in 2003 as Icold Bulletin number 126. Now, it's very significant to note that Bulletin 126 had the highest print numbers of any Icold bulletin to that time and was translated into more languages than any other. And this really serves to indicate the importance of a modern, state-of-the-art bulletin published by Icold covering roller compacted concrete for dams. So Bulletin 126 now relates to industry practice and technology from 15 to 20 years ago. And since publication of the bulletin and work on the bulletin 126, RCC has essentially replaced conventional mass concrete as the conventional material and method for the construction of concrete gravity dams. So RCC is a particularly important dams technology, and Icold bulletins must represent and present the state of the art in the particular aspect of engineering. Now, success in RCC dam construction is not often realized, and the bulletin on RCC is consequently a very important document in enabling successful RCC dam implementation. So, with different technologies in RCC having developed in different places and in different ways, Bulletin 177 was considered as an opportunity to create a certain standardization in the terminology used for RCC dams. And for clarity and consistency, the terms lean RCC and high-paced RCC are no longer to be used, and the following terms have been adopted for the bulletin. Low cementitious RCC, so LC-RCC, this being what might have previously been termed a lean RCC, with total cementitious less than 100 kilograms per cubic meter. Medium cementitious, MC-RCC, with total cementitious materials between 100 and 150, and high cementitious RCC, HC-RCC, which is RCC with a total cementitious content exceeding 150 kilograms a cubic meter. The term pozzolan was replaced in the latest bulletin with the term, more modern term, supplementary cementitious material, and a particularly important change was made in the definition of paste, with cementitious paste essentially being cement, supplementary cementitious materials, chemical additives, water, and entrained air. This can be compared with total paste, which represents essentially cementitious paste plus the non-cementitious fines. So all of the material with a grading of less than 75 microns is included in essentially in the total paste compared to the cementitious paste. A key requirement for the new RCC bulletin was to include the various recent developments in RCC technology, which include developments in the understanding of the early behavior of roller-compacted concrete, design differences in roller-compacted concrete compared to conventional vibrated concrete dams that relate to horizontal rather than vertical construction, developments in RCC mixed design, developments in RCC construction technologies, developments in RCC arch dams, and developments arising from the use of RCC in more extreme environments than had been covered in the previous RCC bulletin. Under the heading of key developments in RCC technology, I will only discuss in this particular presentation developments related to an improved understanding of the early behavior of different RCC types and issues directly related to the design of RCC dams and the design of arch dams, RCC arch dams, will be addressed later in the presentations, while developments in RCC materials, mixed design, construction, quality control, performance, and other uses will be addressed in the later presentations by other presenters. So, to talk about the early behavior of RCC in large dams, research and observation has demonstrated that different types of RCC indicate different levels of early stress relaxation creep. Now, to explain this and to develop this principle a little bit further, I would like to basically give a very broad and basic definition of what is stress relaxation creep. So as we all know, cementitious materials hydration is an exothermic reaction during which cementitious materials gain strength and increase in elastic modulus. And in the consequential temperature rise, the immature concrete attempts to expand, rising in temperature, thermal expansion is experienced. But this expansion is constrained by the surrounding material in the mass concrete that is trying to do exactly the same thing. And so the immature concrete experiences compression. And during this process, the cementitious paste is suffering chemical shrinkage, resulting in an overall loss in the volume of the matrix. So chemical shrinkage occurs due to the fact that the product of the hydration process is smaller in volume than the constituent materials. And chemical shrinkage is not seen in reality. In reality, autogenous shrinkage is seen. So as the hydrating materials gain strength, they get to a point where the shrinkage no longer occurs because there's adequate strength to prevent the shrinkage. And what we see in reality is autogenous shrinkage. But within the matrix, that shrinkage is still occurring, and consequently we end up with a situation where shrinkage is taking the form of creating voids or macro pores within the cementitious paste. With low strength, voids developing within the concrete and compression being experienced through temperature gain, the concrete relieves the compression stresses through creep, or a form of inward collapse, which is stress relaxation creep. So in dam engineering, we usually consider this effect in terms of temperatures. And the common assumption is that stress relaxation creep is approximately equal to the expansion that would occur due to the hydration temperature rise. So stress relaxation creep is a shrinkage or an effective volume reduction, and essentially can be considered as if we have a zero stress situation at placement, temperature T1, and approximately at T2, we again have this zero stress state. And consequently, we have a reduction in volume that is equivalent to the difference in the thermal expansion that would have happened in a mature concrete. Typically in conventional concrete, this is assumed to be of the order of between 150 and 250 microstrain of effective shrinkage. Research in RCC dams has, however, demonstrated a quite different picture of stress relaxation creep than typically accepted in conventional mass concrete dam engineering. With fly ash-rich RCC of a high workability consistency, particularly indicating low stress relaxation creep of the order of a maximum of 50 microstrain and even significantly less. And some low cementitious content RCCs, however, actually indicate higher stress relaxation creep than is typically evident in conventional mass concrete. So this low stress relaxation creep, when applicable, is obviously particularly beneficial in RCC arch dams. And in some cases of high workability fly ash-rich RCC, the stress relaxation creep has been so low that substantial upstream movement has been measured during the construction in the case of arch dams. Various approaches have been used to account for the effect of stress relaxation creep in thermomechanical analyses of RCC dams, such as translating thermal expansion strain into a stress on the basis of the evolution of the concrete elastic modulus. So in other words, with early expansion occurring at a low elastic modulus and subsequent thermal shrinkage happening at a high elastic modulus, the difference between the expansion and shrinkage subsequently has been considered to represent a change in volume equivalent to the stress relaxation creep. However, this approach and others are completely incorrect, and they misunderstand the stress relaxation creep process. So very importantly, an approach based on elastic modulus variations or directly related to temperature will be incorrect, because stress relaxation creep is in fact proportional in the particular material to the level of stress rather than elastic modulus at a particular time or directly relationship with temperature. So the latest thermomechanical analysis techniques for RCC use a stress-dependent stress relaxation creep function, which establishes the distribution of stress relaxation creep throughout the structure at the T2 maximum hydration temperature. And this consequently enables an evaluation of the anticipated extent of expansion that will occur in different parts of the structure during construction due to a low stress relaxation creep. And this expansion effect can be modeled as a concrete pre-compression function in an arch dam, which relates to a progressive lengthening of the arch length with height as the arch becomes progressively more flexible as part of the structure. And this effect reduces the arch radius and increases the arch aperture, effectively consequently further mitigating the long-term effects of temperature drop load in the dam. Furthermore, a conservative assumption of stress relaxation creep in conventionally vibrated mass concrete dams is fully appropriate, with the vertically constructed independent monolithic blocks shrinking away from each other to a greater or lesser extent, and all load during construction of each monolith being carried directly down to the foundation beneath that monolith alone. This is not the case in horizontally constructed RCC dams with induced rather than formed contraction joints with a rough corrugated surface formed and low levels of stress relaxation creep, implying that there are in this foundation material beneath is lower than the associated hydrostatic pressures in the water. Simplicity. This is a point that will repeat and repeats throughout the new RCC bulletin. It is simplicity of design that leads to simplicity of construction that allows full benefits of RCC construction to be realized in the dam. And the location and arrangement of the outlet works must be designed for minimum impact on the RCC construction. This is actually the same for all inclusions in the dam: galleries, shafts, conduits, etc. And particularly important is the inlet tower, and it must be designed for rapid construction and designed specifically to not impede or impose any restraints on the RCC construction. Many RCC dams have been designed such that the construction rate of control for the dam is controlled by the rate of construction of the inlet tower, and that is simply incorrect RCC dam design. To conclude with a few additional issues, the critical weak points on a concrete dams are the joints between concrete placements. And whereas these joints, lift joints, are approximately 3 meter spacing in a conventional mass concrete dam, they are typically every 300 millimeters or 1 foot in an RCC dam. And this must be adequately understood in the RCC dam design and construction quality control program, with the specific bond between layers being designed in accordance with the dam design requirements and the quality control program being configured to achieve those bond requirements universally. Thank you very much for your attention and the opportunity to be able to present to you as part of your workshop this morning.
Indian National Committee of Icold for the organization of this event, and grateful thanks for your kind invitation to take part in this workshop on RCC dams. The title of my presentation is Materials and Selection of RCC Mixture Proportions. We will focus on latest developments related with this subject that are discussed in chapters 3 and 4 of the new Icold Bulletin 177 on RCC dams. Since the previous bulletin was published by Icold back in 2003, a number of trends have been observed in the specifications of the materials and mixes that are used to build new RCC dams, and generally speaking, they improve the in-situ quality of the concrete and provide higher efficiency and economy to the construction of modern RCC dams. This is the list of main topics included in the presentation. After a brief introduction, some key specifications of cementitious materials, aggregates, and most commonly used admixtures will be discussed. Then details of the RCC workability are presented, followed by a summary of the typical mixture proportions of 4 different mix design approaches. Special attention will be given to the recent and successful development of immersion vibrated RCC mixes, and finally typical mix parameters will be discussed schematically before drawing some conclusions. Introduction. In this introduction, we'd like to give attention to the fact that the use or not of a supplementary cementitious material, SCM, in the mix, these are, for example, fly ashes, natural puzzolans, or slag, that such use or not will guide the most probable dam design approach followed by the designers. As discussed in the introduction of the bulletin, 2 primary dam design approaches for RCC dams can be followed. First, the separate approach, where the RCC mix will not have by itself enough in-situ quality required for a concrete dam, and thus not just RCC but bedding mixes are additionally placed on the joints between the layers to give bonding strength, and also some kind of watertight element is required on the upstream face to provide impermeability to the dam. RCC mixes in a separate approach make no use of SCMs or very little. They have the main disadvantage of the less efficient placement, with more sophisticated planning of a greater number of activities running at the same time during construction. Therefore, typically slower production and higher overall cost. On the other hand, the RCC mix in an all RCC dam approach will make extensive use of fly ash or pozzolan, and the mix can be designed to achieve by itself and without bedding mixes and without upstream elements the desired strength between the layers and the required impermeability for the concrete dam. This must be recognized as the simplest and most efficient methodology for the construction of high-quality concrete dams. RCC types are also classified by the total content of cementitious materials in low, medium and high cementitious RCC, with respective limits in 100 and 150 kg per cubic meter as indicated in the table. Some typical strength values at 1 year age are included in the table for each type. The lower values of the column at the left side corresponds to low cementitious, less than 100 kg per cubic meter, which is mostly associated with the RCC mixes used in the separate dam design approach. On the right column, you can see the values associated with the high cementitious mixes that are typical of the more efficient all RCC dam approach. As can be imagined, a wide range of possibilities for less demanding mixes is also available in the medium cementitious mix in the middle of the two. Before moving into the materials description, it should be recalled that the Icold Bulletin 165 on the selection of materials for concrete dams, published in 2013, addresses the primary selection requirements for materials for all mass concrete dam types, including RCC, and therefore only issues of particular importance in respect of current RCC practice are addressed in the new bulletin on RCC dams. Cementitious materials. Laboratory testing of different potential sources of cementitious materials is necessary at an early stage of the planning, done by the designer to ensure that the concrete performance meets the design criteria. This diagram shows the proportions of the main chemical components of Portland cement and various supplementary cementitious materials. Low lime fly ash, type F, and natural pozzolan are by far the preferred ones. Aggregates. The typical combined gradations ranges of aggregates used in high and low cementitious RCC mixes are indicated in the table and represented in this figure. 3 comments. First, there has been a clear trend in recent years to reduce the maximum size of aggregate from 80 millimeters or even higher used in early times down to 50 or 40 millimeters. The aim is the need to control segregation, especially in the low workability mixes and for rounded aggregates. Second, a slight higher percent of sand or fine aggregate in the low cementitious content RCC, LC-RCC, compared with the HC-RCC. And number 3, the increased amount of non-plastic fines below 75 microns in any type of RCC, although some plasticity might be accepted in LC-RCC under certain limitations. This figure shows the example of a high cementitious mix. The aggregate split of the combined gradation, which is shown in black in the figure, is 30%, 35%, 35%. Based on 2 coarse aggregates, 40 to 20 millimeters and 20 to 5 millimeters, which are represented in red and green color respectively, and just 1 fine aggregate, which is in blue color, with a high proportion of fines in it, between 12 and 18% in this example. A second fine aggregate grading is also shown in orange color, which corresponds to a typical washed sand specified for conventional concrete. The difference between both gradations can be clearly appreciated. Admixtures. A set retarder is nowadays the most popular admixture used, especially in high workability RCC mixes. The primary objective is to delay the setting time of the mix in order to be able to place the next layer within the initial set of the surface of the receiving layer beneath. The use of super retardant mixes, initial set of 20 hours or even more, is one of the key features of modern RCC mixes placed in large areas of, say, between 15 and 20,000 square meters without any surface treatment, achieving a good bonding, which is the hot join. This provides a huge placement efficiency, which is typical of the all RCC dam approach. An additional benefit is obtained by using these admixtures associated with the secondary effect as water reduces. Based on setting time tests made in auto conditions and according to ASTM C403, the figure shows the average relationships found in a particular project between the mean ambient temperatures and the initial set for different dosages of the retardant admixture. In this example, the line in black shows the selection in steps of increasing dosages of the admixture so as the ambient temperature rises, in order to keep at all times the initial set between 15 and 20 hours. However, the actual surface condition of the lift joint must be visually inspected at the placement by experienced supervisors to confirm the test results. The setting time is affected by other parameters, wind, humidity, mix workability, and so on, that are not always well identified in the test. These photos show typical good fresh condition of a workable and super retarded RCC. Note the print of the tires of the trucks used for the transportation of the RCC for the next layer. This is a good sign of the desired hot condition and a monolithic bonding. And in order to provide durability to the exposed surfaces of RCC dams, especially in cold climates, a number of commercially available air entraining admixtures have been successfully tested in a recent project with a very workable RCC mix. Dosages between 0.5 and 0.6% of the cementitious materials have achieved a very consistent air entraining between 4 and 7%, as shown in the figure above. Consistency. Consistency, as measured in fresh RCC with the loaded VB test ASTM C1170 procedure B, is a key control feature during placement. The procedure should be slightly modified with full filling of the mold and avoiding any pre-compaction for very workable mixes, VB times below 12 seconds. Following the consistency test, the time of vibration in the test can be extended up to 2 minutes, and this produces a similar compaction effect, or just slightly below, as achieved by the rollers in a real placement condition of the 300 mm thick layers. Therefore, the test allows the evaluation of the amount and quality of paste that is brought up to the surface during vibration on top of the disc, as shown with the number 2 in the figure. This is an excellent evaluation example of very good paste. Then it is all collected back into the recipient, and the density can be measured. The line diagram at the bottom right corner shows the position of different RCC mixes relative to the VB time, with stiff mass CVC on the left end. It should be noted the general reduction of this value in modern RCC mixes of all types compared with early times. Typical mixture proportions. The average mixture proportions of the cementitious paste for different RCCs are included in this table. The content of Portland cement is considered to be similar regardless of the RCC type. As has been mentioned before, the use of an SCM such as fly ash or pozzolan is a distinctive factor between low and high cementitious RCC, and the difference in this case is in average circa 100 kilograms per cubic meter. With regard to the free water content, it should be noted that the less workable low cementitious mixes, VBs up to 30 seconds and even more in early RCCs, is, however, higher than the workable mixes with VB times below 15 seconds. It seems to be a contradiction. This actually shows that a significant level of workability can be achieved through optimization of the aggregates and the additional gain in workability provided by the use of pozzolanic materials and admixtures. This is even more evident when comparing the average water cementitious ratio of the low against the high cementitious RCC. While the mean value of 0.57 of the high cementitious RCC in the right column is considered to be typical of mass stiff concrete, a water cementitious ratio of 1.51 in the low or even the 0.99 of the medium ones do not seem to follow the basic principles of traditional mass concrete. That is why other items additional to the RCC need to take part in the configuration of the dam in a separate approach. Let's now take some time to introduce key features of IVRCC, Immersion Vibrated RCC. This picture was taken during construction of the full-scale trial leading to the construction of Springgrove Dam in South Africa, completed in 2012. A very workable mix was designed with a VB time between 6 and 12 seconds. The mix has a total content of cementitious materials of 160 kg per cubic meter, of which only 50 kg per cubic meter is cement and the remaining 110 counts for local available fly ash. All concretes in this picture correspond to the same mix, and no grout, no mortar, bedding concrete or conventional concrete mixes are added. The spread and uncompacted RCC is visible on the right near side. The high paste roller compacted surface can be appreciated at the back, and the immersion vibration against the front face is running on the left side, followed in this particular layer by a handheld vibrating screed easily finishing the top surface of the future downstream steps. Immersion vibration is achieved without adding any grout and whilst the RCC is still fresh. The use of the set retarder helps also on this task. This is called immersion vibrated RCC, the most simple and efficient way of building modern RCC dams and its interfaces either against formwork, rock abutment, embedded elements or dam instruments. Immersion vibration crosses the 300 mm thick layers and penetrates in total around 500 mm down into the concrete as shown here. In hot condition, when the second lower layer has not initiated set, this leads to a complete interpenetration of both layers and the elimination of the physical joint plane between them, achieving an excellent bonding and impermeability. This has been investigated by testing cores drilled in this and in the area compacted by the rollers. An excellent lift joint behavior has been observed in both cases. The key features of materials and mixture proportions of IVRCC mixes are listed in this slide. Most of them apply to modern super retarded high workability mixes, as has been mentioned before. Special attention should be given to the optimization of the fine aggregate in order to achieve a well-graded material and a compacted void ratio as low as possible, ideally below 30%, as this will reduce water demand and the required volume of cementitious paste in the mix. Example pictures of completed IVRCC dams are shown on the left. This is the excellent aspect of the stepped face built with IVRCC at the Hoop Dam in South Africa. And here a general view of the dam near completion. Just one RCC mix and no grout or conventional concrete against the faces or anywhere else. This is the completed Springgrove Dam for which the full-scale trial was shown before. And this is a Siso Dam in Spain, a 103 meters high dam that has been recently completed and that is at present at the final stage of impoundment. The dam is showing an excellent performance and no seepage through the concrete. The same RCC mix that is roller compacted in the core is consolidated by immersion vibration at the faces against gallery walls, a detail is shown here, and against the rock with excellent performance. Vibrators mounted on an excavator manage high production and best quality. This is a recent experience with air-entrained IVRCC. Note the high workability, rich in paste mix, and after immersion vibration on the right strip against an inclined formed face. And this is a trial in which 3 different ways of forming the faces have been compared: conventional concrete, grout-enriched RCC, and immersion vibrated RCC. No real differences between them. But IVRCC is much more simple and cost-effective option. In this particular case, the RCC mix was also error trained. Finally, let's summarize some mix parameters. Consistency, as shown before. The drier, low cementitious RCC used in early days has moved to the left of the diagram below 30 seconds now, and on the other end, high workability mixes below 15 seconds and IVRCC below 12 and down to 6 seconds, touching the limit of zero slam CDC mixes. In-situ density continues to be higher in high cementitious mixes. Note the best density of IVRCC when roller compacted, in average higher than 99% of the theoretical air-free density, and slightly lower when vibrated by immersion, similar to conventional concrete mixes. The total paste volume calculated by adding the fines below 75 micron of the fine aggregate to the cementitious paste is nowadays relatively similar in all types of RCCs. This used to be different in earlier times, but the addition of the fines has equalized this parameter. There are some exceptions. On the very right end, the excellent IVRCC mix at Enciso Dam has only needed 17.6% of total paste to achieve consistent VB times below 10 seconds. And the paste mortar ratio, typically related with the void content of the compacted fine aggregate, and exceeding the 10% this VC value in high cementitious mixes, and lower down to 0% towards the low cementitious ones. Conclusions. High cementitious RCC is associated with high supplementary cementitious material content mixes, whereas commonly the low cementitious RCC mixes make no or very little use of such SCM. Water content is even higher in low cementitious RCC. The quality of the fine aggregate below 5 mm, and in particular the aggregate fines below 75 micron, play a major role in the selection of the mixture proportions for RCC mixes. Key common features of all kinds of modern RCC mixes are a reduction of the maximum size of aggregate below 50 mm to control segregation, a volume of total paste, including aggregate fines, between 210 and 240 liters per cubic meter, and improved consistency, lower VB times relative to values used in early dams. High workability RCC mixes simplify dam construction and achieve best in-situ properties. IVRCC, a mix that can be consolidated either by immersion vibration or roller compaction, is the most optimized version of very workable and super retarded mixes. IVRCC equals no CVC, no bedding mixes, no grout, just RCC. Thank you very much for your kind attention.
Good morning. I am Rafael Ibañez de Aldecoa, and I am the member of the Icold Committee on Concrete Dams, who was commissioned to lead the drafting of Chapter 5 construction of the new Bulletin on RCC dams, with the support of other members of the Concrete Dams Committee and additional external experts. Chapter 5 construction is a very long chapter, and due to its length and content, I don't have time in 20 minutes to review and comment on all sections and subsections. I will focus on highlighting some of the most remarkable advances and trends related to RCC dam construction technologies since the publication of the previous bulletin in 2003. On each slide, usually at the top right, is indicated the title of the section in which the topic zone is discussed. Let's start with a riddle. Pay attention to the next slide. This is a joke, but it is very representative of how industrial activities usually work. quality, speed, and cost are a trio of features that generally don't work well together at the same time, but only two at the same time to the detriment of the third. But I know of an outstanding exception, RCC dams. Speed, quality, and cost usually go hand in hand, all three together in an RCC dam. This chart illustrates the average placement rates of some 500 RCC dams plotted against the volume of RCC placed. The indicated envelope encloses 97% of all plotted values. As you can see, the upper limit of the envelope has been widely exceeded in some cases, although actually in very few cases. Shocking conclusion that can be drawn after analyzing the chart: less than 10% of the RCC dams have been constructed at an appropriate speed. Let's analyze what is the reason for more than 90% of slow RCC dams, starting with the key factors for a fast RCC dam construction. It seems very easy. We just need a proper design, proper materials, a proper mix, and a proper construction. But in this chapter, let's focus on the latter, construction. A highly experienced contractor is a must to achieve a good quality and fast RCC dam. A contractor who has the knowledge to properly manage all of the factors in the following list. A mistaken decision regarding any of the factors on this list will have a negative impact on the speed of construction of the dam. To maximize synergies between all parties involved in an RCC dam project, in the new bulletin we encourage the adoption of procurements entailing an early contractor involvement. Full-scale trials is a new section in Chapter 5 of the new bulletin. For large to very large dams, we recommend conducting the 3 stages of full-scale trials that you see on this slide. Aggregate production and supply has been the bottleneck hindering the speed of construction on a significant number of RCC dams. The aggregate processing plant must be properly dimensioned, and if there is space available for large stockpiles, it is advisable to have 30% to 40% of the total required aggregate produced and stockpile prior to start RCC placement on the dam. Depending on the maximum size of aggregate adopted, modern RCC dams use in their mixes 3 to 5 aggregate groups, including 1 or 2 sands. The maximum size of aggregate usually ranges from 40 to 60 millimeters, except in China and Japan, where they use larger aggregates up to 75 to 80 millimeters. At the crushing plant, it is very advisable to implement impact crushers for secondary and tertiary stages of crushing, due to they produce better shaped aggregate. The crusher that produces the better shaped sand is the vertical impact crusher, rock on metal type, and the higher cost of this type of crusher will generally be justified due to the important benefits associated with an improved quality sand with lower void content. The type of mixer best suited for the production of RCC is the horizontal twin shaft paddle type batch mixer that has been utilized on nearly half of the RCC dams completed to date, with a significant increase compared to the 35% stated in the previous bulletin as indicated in square brackets. Cooling and heating techniques is a new section. In the previous bulletin they were included in the design chapter and now have been moved to construction, and an exhaustive list of the different methods available has been put together, classifying them into 3 groups. The first group is called passive cooling methods. Passive methods refer to cooling or heating the RCC or some of its components with little or no energy consumption. This is the list of passive cooling methods. The second group is pre-cooling methods. Methods in red mean they are new with respect to the previous bulletin. Some examples of the most used pre-cooling systems. At Portuguese Dam, in the Caribbean island of Puerto Rico, the requirement for the maximum placing temperature of the RCC was 15.5 degrees Celsius, and the pre-cooling systems implemented were flaked ice makers, wet belts, and water chillers to cool the water for the wet belts and also the missing water required at the batch plant to manufacture the RCC. In this slide, we see close-ups of a water cooling plant and a wet belt. And in this slide are shown some pre-cooling systems based in the use of cooled air instead of cooled water. The third group of cooling systems involves the post-cooling methods. As these specific methods are mostly implemented in arch dams, they are thoroughly discussed in Chapter 9. With regards to the heating methods, as well there are passive heating methods, preheating methods, and post-heating methods, but due to the time constraints, I skip listing them. Please refer to the new bulletin. With respect to RCC transportation, no particular innovations since the previous bulletin. For large to very large RCC dams, the most used systems are high-speed belt conveyors feeding tracks on the dam surface, or more sophisticated all-conveyor systems like the one we are seeing in these photos. In this extremely large RCC project in Ethiopia, a peak daily placement of 18,500 cubic meters and a peak monthly placement of 250,000 cubic meters of RCC were achieved. In some cases, the so-called vacuum chutes have been successfully used, a very low-cost gravity conveyance system to transport RCC to tracks on the land surface. Here we see two examples. With this system, appropriate, very cohesive RCC mixes are required to avoid segregation. In the new bulletin, we have included a new section to describe the different possible overall placing methods that can be used to construct an RCC dam. The horizontal placement represents the simplest placing methodology. Consecutive horizontal layers are placed from one abutment to the other in one or several lanes. The slope layer method. The main advantage of this method lies in decreasing the area of the working face to ensure the placement of relatively small successive layers before the initial set of the receiving layer, while avoiding the need for significant set retardation. Next is the split level method. The dam is placed in two halves with staggered lifts placed alternately on each half. Typical lift heights range from 3.6 to 10.2 meters. Ramps are needed to shift equipment from one half to the other. They can be metal ramps or RCC ramps, as in the example in the picture. The block placement method. On very large RCC dams, placement can be split into blocks using transverse formwork, as applied for Longtan Dam in China. Each construction block will generally include several contiguous monoliths, separated by induced joints during the RCC placement process. This method has also been applied for several dams, not very large, where the concrete plant capacity was insufficient to allow a more efficient approach. And the last one is the non-continuous horizontal layer placement method. This method has been used for only a few dams, but with successful results. The method involves placement to the full height of a lift over an area sized such that placement of successive layers is achieved before the initial set of the receiving layer. Let's move to spreading and compaction. Please pay attention to the aspect after compaction of high cementitious and very workable RCC mixes, with a BB consistency around 12 seconds. Plenty of paste has been expelled from inside the layer to the surface. Tire tracks are clearly visible, as are people's footprints in the next picture. After getting this very nice surface look, now the secret to achieve a good bonding with the subsequent layer, that is to say a good hot joint, is to maintain this shiny aspect over the whole layer surface by curing with a mist of water until the next layer is placed on top of it, which must be done before the initial set of the receiving layer. Regarding the layer thickness, 300 millimeters is the value mostly adopted. In this picture, we have the opportunity to see what normally we cannot see, the interior of the concrete mass. It is a full-scale trial that has been cut vertically. And what do we see? We see that in general, we cannot discern the horizontal joints between layers, which means that most likely we have achieved good hot joints except in one joint. And what has happened here? It could be any of the following causes or a combination of them. During the first 2 decades of RCC dam construction, approximately until the end of the last century, in most of the RCC dams, 12 to 15 tons double drum vibrating rollers were used. But later on, it was found that 10 to 12 tons single drum vibrating rollers are more adequate. They have higher dynamic force, achieving better compaction at the bottom of the layer, therefore less possibility of the honeycombing that we have seen in the previous slide, and also achieving better interpenetration between the bottom of the layer under compaction and the receiving layer. Nowadays, modern compactors are fit with intelligent compaction technology. The success of the quality of an RCC dam lies in the quality of the horizontal joints between layers. Therefore, it's crucial to specify realistic values for the limits for hot and warm joints. The modified maturity factor approach still is being used, but the most recent approach is to establish the limit for hot and warm joints, respectively, based on the initial and final setting times of the RCC of the receiving layer for the actual weather conditions. Accordingly, hot joint until the initial set time, warm joint between initial and final set times, and cold joint beyond the final set time. The different treatments for the different types of joint are explained in great detail in the new bulletin. The way to find out if we are constructing a monolithic structure is to obtain vertical cores that traverse a number of horizontal joints, not necessarily as long as the examples in these two pictures. From the cores, specimens can be prepared with a joint in the middle to be tested in direct tension. A short video during testing. Let's examine some specimens after the direct tensile test. What is the appearance of the joint after breakage? We can obtain the three following cases. A flat joint, showing that there was mainly only chemical bonding. A very rough joint, showing interpenetration, therefore chemical and physical bonding. And in this third case, the break did not occur through the joint. The value of the tensile strength obtained in the test underestimates the tensile strength at the joint. Due to the method we use for constructing RCC dams, placing consecutively relatively thin layers, we have plenty of potential weak planes in the structure, which are the abundant joints between layers. There are two golden rules. Number one, try to minimize joints other than hot joints. And number two, the rule of the 2-100%. Adequate curing of hot joints is of the utmost importance. This golden rule is the secret, the key, the magic formula to obtain good hot joints and, as a result, successful RCC dams. Curing can be performed manually or with misters, and excess water must be removed manually or with vacuum trucks just prior to placing the next layer of RCC in that area. Another new section deals with the vertical construction joints in a layer, which can be longitudinal between adjacent placement lanes or transverse. Contraction joints. The most commonly used method to form contraction joints in RCC dams is the one that you can see in this video. One of the most significant advances since the publication of the previous bulletin has been the extensive use of the grout-enriched vibratable RCC and grout-enriched RCC for forming the faces of RCC dams, and more recently, the emergence of the immersion vibrated RCC, all of them with the aim of eliminating the conventional concrete. The difference between GERCC and GEBR lies in where we add the grout to the RCC, top or bottom. In cold climates, it is necessary the air entrainment of the facing concrete, either GERCC or GEBR, and this is a topic that requires further investigation. In some recent RCC dams, IBRCC has been successfully used, and also mortar-enriched vibratable RCC has been applied at a few dams. Sequence of performing GEBR. 1. Create small ponds to hold the grout and avoid it being displaced by the bulldozer when spreading the RCC on top of it. 2. Fill the small ponds with grout up to a level indicated by a line in the formwork to ensure the right dosage of grout per cubic meter of RCC. 3. Spread the RCC on top of the grout next to the formwork. 4. Vibrate the GEBR next to the formwork. 5. Roller compaction of the interface GEBR RCC and the GEBR next to the formwork with a small double drum roller. 2 short videos performing GEBR. You can see that abundant grout has appeared on the surface going through the RCC from bottom to top. Adding grout, the RCC has been transformed into conventional vibrated concrete, but with properties more similar to the RCC and a perfect interface between them. 2 pictures performing IBRCC. Due to the low BB consistency of the IBRCC, around 6 to 10 seconds, immersion vibration is possible without adding grout. An important advantage of the IBRCC is the no need for additional resources and personnel for production, transportation, distribution, placement, and quality control of the grout. This is a self-explaining slide. We are working next to the formwork with bulldozers, rollers, excavator with gang of vibrators, etc. We need sturdy panels. Regarding the methods for forming the galleries, same as for the dam faces, GEBR, GERCC, or IBRCC against formwork are the preferred systems in modern RCC dams, among many other possible methods and solutions explained in the new bulletin. two pictures of a gallery constructed using GEBR against formwork and precast concrete soffits for the ceiling. The interior of a gallery formed using reinforced GEBR against formwork and precast concrete soffits. As you can see, the finishing of the walls is similar to conventional vibrated concrete. And to finish, regarding the curing and protection of the RCC, we have expanded mainly in addressing the measures to be taken under cold weather conditions. As a final remark, I recommend to all those interested in RCC dams to read and have at hand this very comprehensive new bulletin. Thank you very much for your kind attention, and also thanks to the Indian National Committee on Large Dams for inviting us to participate in this splendid workshop.
Good morning, ladies and gentlemen, and welcome to my presentation on RCC quality control. I would like to focus on the challenges and implications for RCC quality control, address RCC full-scale trials, accelerated curing, and then conclude with some points on the value of RCC quality management for the project economy. All dams are susceptible to the effectiveness of the quality control achieved during construction. Therefore, a quality management system as a critical part of ensuring construction quality must be put in place as a requirement for all RCC dam construction works. A quality management system consists of quality assurance, addressing processes, and typically is the responsibility of the owner. And then the quality control, so that's the activities such as the testing, which are typically the responsibility of the contractor. The quality program always needs to be project specific to ensure that the particular materials and circumstances unique to each RCC dam project are effectively addressed. It also needs to be well formulated with developed quality objectives and criteria to become that invaluable tool allowing on-the-fly decision-making during the RCC construction. The Icold Technical Committee on Concrete Dams has produced two bulletins in which quality control of RCC and more general of dam concrete are discussed. That's the very fresh bulletin number 177 on RCC dams, in which quality control is discussed in chapter 6, and the earlier bulletin 136, which is dedicated to the specification and quality control of concrete dams. So, what are the challenges and implications for quality control of RCC in particular? Well, one challenge is the construction in single layers over very large areas, shown in the two left images. Compared to CVC dam construction, shown in the right image, that results in a tremendously larger number of RCC lift joints. So, as a comparison, the two RCC placement areas in the two images on the left are around 250 by 40 meters width in the very left case, and around 120 by 100 meters in the center image, whereas in the CVC dam construction those block placements are typically 15 to 20 meters wide and probably 30 meters or so in upstream, downstream direction. Another challenge with modern RCC is the large proportion of fly ash and natural pozzolans as supplementary cementitious materials, resulting in slower strength development, as shown in the top graph with conventional mass concrete in blue, compared to a high cementitious RCC in red. On top of that comes high range set retardation, which has become common with modern RCC. Let's look at the construction progress at the Lai Chau RCC dam in Vietnam as an illustration of the challenges for RCC quality control. At the time when the first RCC has reached the specified design age of 365 days, more than 1 million cubic meters of RCC had been placed, and the first RCC was covered under something like 100-meter high concrete. So one really needs to make sure that the RCC down here will comply with the specified performance criteria. It is obvious that traditional quality control with concrete strength using sampled specimen is not effective in RCC, as it would provide only a retrospective verification. Therefore, RCC construction requires proactive monitoring and control of all aspects of the RCC construction to allow an extremely early understanding whether the placed fresh RCC and lift joints will meet the specified performance, or whether corrective measures have to be implemented, and then of course also which ones. That includes control of each of the constituent concrete materials and moisture contents, as well as check and inspection of all the processes and activities. Now in practice, this proactive monitoring and control of all aspects of the RCC construction is realized by establishing various control points at the site, where supervision, monitoring, and testing processes and activities are conducted. So again, exemplifying Lai Chau in Vietnam, that was incoming materials like cement and fly ash verified through the supplier's testing certificates, then occasional third-party verification checks, then quality of source rock in the quarry, so that includes quarry management and then testing the rock properties, going through the crushers from where the quality of crushed aggregates will be monitored. Then all that is going into the batch plant, from where the quality of the batched RCC is checked. Then along the delivery line at the placement, the quality of the delivered RCC at the placement. Then the quality of the fresh compacted RCC, so fresh properties, and then eventually quality of hardened RCC by coring. An integral and essential part of the quality plan for all RCC dams is the full-scale trial, or FST. Using the supervisors, plant and equipment operators and other key staff, the equipment and methodologies intended for the dam, the full-scale trial must be continued until all RCC placement methods and procedures, and that includes the quality control activities, are reasonably perfected. That may include the construction of more than one full-scale trial, as is illustrated on the left side. The first purpose of the FST is training, and training under site conditions, and that includes rain and night shifts. And it is very beneficial if the contractor has exercised the particular challenges coming through rainy seasons and also night work outside the dam before start of the construction. The FST is also used to refine correlations between RCC properties to serve as an initial database as the basis for the quality control at the start of RCC dam construction. The verification of RCC performance, placement procedures and methodologies includes the recovery of RCC cores from the FST for testing, typically after 90 days or sometimes also at later ages. So the left image shows a core from an RCC trial embankment along with the qualitative classification of lift joints from a visual assessment of the core. The core testing then allows verification of the lift joint properties as a function of the lift joint maturities and applied lift joint treatment methods. And this verification is used in the final specification of the lift joint type maturity limits and the associated treatment methods. This is illustrated in that right-hand side graph, where the 365-day direct tensile strength across lift joints is put over the so-called modified maturity factor for different joint types: hot, warm, cold, and also super cold joints. And in this case, the in situ characteristic direct tensile strength across lift joints was 0.8 megapascal. And one can see here for hot joints and cold joints the indicated maturity limits for those kinds of lift joint types. Another emphasis of the full-scale trial embankment is on the evaluation of the initial and final setting times of the full-scale batched RCC, as sometimes the retardation admixture performance in the laboratory can be quite different from that of batch plant batched RCC. For the purpose of getting an early understanding of the long-term strength development of concrete, the accelerated curing procedure under elevated curing temperatures has been developed some time ago and has become commonplace in testing RCC. Typically, and depending on the type of supplementary cementitious materials used in the RCC mix, 7-day or 14-day accelerated curing periods are applied. That means the periods during which the RCC specimen would be cured in a hot water bath. The accelerated curing temperature of that hot water bath is often applied at 90 centigrades. Generally, the 7-day accelerated curing period at 90 centigrades simulates standard curing maturities anywhere between, say, 90 and 180 days, whereas the 14-day period simulates anywhere between, say, 100 to somewhere above 365 days. In the case of the example presented in the chart on the right, the 14-day procedure simulated pretty well the 180-day compressive strength under standard curing conditions. Essentially, accelerated curing provides a greater early confidence that the RCC long-term strength will be achieved, and also provides greater confidence in specifying RCC target strengths at late design ages. I would like to close with pointing out the value of RCC quality management for the project economy. Consider that the perceived level of quality control drops from good to poor, typically indicated by a considerable increase of the coefficient of variation in the testing data. The consequence of such change may be that, as a practical example, 10 kilogram of additional cement per cubic meter of RCC would be required to meet the specified characteristic strengths. It is clear that this results in additional cost to purchase this additional cement. And as a practical example, this could be around $1 million for 1 million cubic meters of RCC still to be placed. However, this tangible cost will dramatically increase with the consideration of concomitant cost, for example, from the need of additional temperature control measures addressing the increased hydration heat caused by those additional 10 kilograms of cement in the mix. The potential drop of setting times may require additional retarding admixture to be added, or the potential drop of setting times may even lead into increased efforts on lift joint preparations if more warm joints are encountered on the placement. And especially that latter situation may result in slower progress and even construction delays. There may be an increased risk of compromised RCC lift joint properties, and in certain situations, there may be increased maintenance and even need for remediation once the dam is in operation. Therefore, investing in proper quality management will always pay off in RCC dam construction. Thank you very much for your interest in that presentation.
the vacancy was clear.
Presentation come. Is that coffee break now? Mute.
कॉफी ब्रेक तो हो चुका होगा इनका.
कॉफी ब्रेक अनाउंसमेंट डिस्टर्ब नहीं होगा. ये नहीं वो तो कर रहे हैं.
बहुत जरा मेरा हॉल 7 ज्वाइन करना जरा अपने ये बंद कर दो सब बंद कर दो हॉल 7 हॉल 1 ज्वाइन करो जरा तो हाँ मैम कौन सा हॉल 1 में मैम बोल पूछ रहा हूँ क्या चलाना है क्योंकि
कुछ नहीं चल रहा इनका टी ब्रेक तो नहीं चल रहा है इसने अनाउंस किया था राफेल ये राफेल की नंबर 5 की चलेगी प्रेजेंटेशन होगी
मैम प्रेजेंटेशन होगी टोटल 6 होगी 6
अच्छा मार्को का भी हो गया
हाँ
इन्होंने कहा था हमें 5 के बाद ब्रेक लेंगे सर ये ब्रेक तो नहीं लगा कहीं
मेरे ख्याल में
May I ask you to please announce the length of the coffee break also in English? I think there are quite a number of online attendees who otherwise do not get this information.
15 minutes break for coffee. Hello, we can have 15 minutes break for coffee. Hello. Hello.
I think this was scheduled in. Was that scheduled in?
It is generally means not everybody prefer for that, but if you want it can be 15 minutes break, no problem for that.
I'm fine with continuing, as this may provide more time for discussion. What do others think?
No, if you want coffee break, we can break for 15 minutes. No problem for that.
Sunil, I think it'd be best just to continue with the presentations so we have more time.
Okay, no problem. That also we can do.
Okay, is there a problem with the presentation for chapter 7?
Okay. So we can take it next presentation in that case.
So the next presentation will be chapter 7.
Yes, we can take
From
that
Mr.
one.
Dolan.
If there is a problem with the chapter 6, then we can have that chapter 7.
Chapter 6 was finished. Chapter 7 is next.
Okay.
Yeah, it's the prefix 06.
Oh, I'm sorry. Yes, prefix is 06.
Actually, chapter 7 is not audio possible. मैम चैप्टर 7 में आवाज नहीं क्या करूं आवाज वीडियो नहीं है पीपीटी है क्या करूं ठीक है भाई क्या डालना ये लाइव पे जा शेयर कर रखना है हां उसमें जाकर फॉलो कौन सा आइटम लेआउट पे नहीं यहाँ पे होस्ट लेआउट पे वाली आईडी पे इधर आकर नीचे 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 3 डॉट होंगे नहीं इधर नहीं पार्टिसिपेंट के नीचे जाने ऊपर वाले में इधर 3 डॉट है रिक्लेम होस्ट है अरे इसमें उसमें होता है ऊपर जाओ तो पार्टिसिपेंट में जाओ ऊपर उधर जाओ तो और लेफ्ट में हमारे
हाँ मैसेज कर दो या बात कर दो
Hello. Hello, Mr. Roger. Hello.
Yes, I'm here.
Yes, sir, this we have the presentation and speaker is also live, but there is no sound in that. So I think we should ask the speaker, either he present live because there is no sound in his presentation.
Okay. So,
we have the presentation.
Okay. So Mr. Dolan is
Timo?
on the line, and so he can make the presentation. If Tim, would you like them to have the slides showing, or do you want to present from your computer?
Whichever works best.
Okay, so Neil, why don't you have your officer put up the slides and Tim can just say next.
We will play the presentation.
And he will say next for each slide.
Okay.
Okay, good day to you all. Not exactly sure why it doesn't show sound because I can see that right above the one there. My name is Tim Dolan, and as an introduction, I've been working on RCC dams for almost 40 years. And as a part of that, I've been on site in construction. I've done mixed designs and been involved from the beginning to the end and have evaluated RCC dams from as early as 28 days age to the performance at 24 years age. So I'm familiar with all of the different methods of construction and low, medium, and high cementitious mixes. Can you go back? Okay, I'll start with the early RCC dams. Some of them were less than satisfactory. The RCC dam performance can be improved with careful attention to the practices summarized in this updated report. Two of the principal issues of the early dams were seepage of poorly compacted lift lines due to less workable mixtures and leakage due to cracks from lack of induced contraction joints. Modern dams have had satisfactory performance due to utilizing more workable mixtures with a VB consistency generally less than 20 seconds, improved understanding of lift surface exposure criterion and the use of set retarding admixtures, improved methods and equipment for dam facing and contraction joints, and RCC dams now have the performance equivalent to conventional CVC mass concrete dams. Next. Okay. Some of the terms here, including hot joints, they have some roots in conventional mass concrete. The hot joints are equivalent to the layer joints in a conventional mass placement, whereas the cold joints are the exposed joints where you're placing onto hardened concrete. Next. Sloping layer method has some similarities to those original mass CVC constructed dams. However, sloping layer generally goes from one abutment to the other, eliminating the traditional block construction approach. On my last dam, it took about 3 weeks to complete one placement from one abutment to the other. But they have the hot joints, multiple hot joints that are placed, generally built up to 3 meters, with cold joints prepared prior to and afterwards. Some are even hybrid dams. Raphael mentioned some of those that show multiple types of construction, hot joints on hot, and then delays for the middle. Okay, the requirements for lift line performance are that the mix must have a consistency suitable for compaction. Hot, warm, and cold joints must be classified, and appropriate lift surface cleaning and preparation techniques are done. This may go from either no treatment or air blowing to vacuum of lift surfaces to brooming either on warm joints or as a pre-treatment for cold joints, followed with bedding mortar and grout. The effects of RCC production can vary from none to very significant, but generally what's good for production is often good for performance. The fresh properties greatly influence the ultimate dam performance. That includes the workability of having suitable consistency. The lower VB times give you better mixing efficiency and the use of ability to use admixtures and almost eliminate segregation. And this results in uniform density of RCC from the top to the bottom of the lift. Time of set has a great influence on lift line performance, as we've seen. If you continue to have hot joints, you will have very good performance. It gives you a longer time for compaction. It allows you more time to get the RCC facing interface consolidated, and the hot joint time is extended. But I will give you some caution on extended set times. There is more exposure to temperature. There's more exposure to rainfall, and that temperature could be cold. I've had some hot joints go more than 3 days. But from performance, a hot joint is comparable to a mass concrete placement layer. Warm joints, there's some difficulty due to setting time and surface cleaning. Some warm joints, if not properly cleaned, will end up becoming cold joints. Cold joints generally have 80 to 100% of parent performance, concrete performance, with proper cleaning applied to all lifts. There's a significant improvement in performance of low cementitious dams when you're using bedding concretes and mortars. The extended or super cold joints can have very good performance, or it depends on the proper preparation, such as cleaning, brushing, and use of mortar. Performance of drill cores, 90% hot joints were achieved. This is one dam from Myanmar. The middle one from Upper Stillwater only used vacuum. It had no other lift surface treatments and had 90% 90% bonded lift lines. And then below you see where mortar has been applied on all joints. This graph tells you a little bit to the left. You have where there was a mixture with a low cementitious dam. It had 24% bonded lift lines, but when you added mortar or bedding concrete to it, it achieved 90% bonded lift joints. The one where you see 64%, that was with a VB time of about 30 seconds. And when the VB time was decreased from 30 to 17 seconds, we achieved 90% bonded lift joints. Next. Next. Using performance based on bonding of drill cores, 90% bond is excellent. This is the equivalent of conventional mass concrete between the lift lines. 70 to 90% bonding is satisfactory and similar to what you see in conventional mass concrete dams. 50 to 70% bonding is less than satisfactory, and less than 50% bonding is unsatisfactory. There may be needs for remediation to be done. Below you see sloping layer concrete that had 100% bonded cold joints. The effective compaction is shown here on the left. Fully compacted RCC had a compressive strength of 23 MPa, but when it was not compacted, it was 80% of its maximum density. The compressive strength was only 21% of the maximum strength. Next. This is a graph. As with any concrete, the more as air gets into it, you will lose strength. Conventional and RCC lose about 4 to 6% strength for every percent of air that could have been removed but was not removed. As you see here, when there's a 10% loss of density, meaning about 90% compaction, you can have a 50% loss of strength. Next. This is based on from a USA database of high cementitious and low cementitious mixtures. The average direct tensile strength of lift lines was about 80% of the parent RCC, and the RCC tensile strength ranged from 3.5 to about 5% of the compressive strength. These are additional results that show you the direct tensile strength of high cementitious, low cementitious RCC. Next. And this is from the results of drilled cores. In this, we have all tests. We have high cementitious RCC. We have low cementitious RCC that has voids, and some of them are small voids. Others are from segregation or lack of compaction. And on the bottom, that same mixture with bedding concrete improved to 90% bonded lift joints and restored the lift line performance. Next. This just shows shear properties of different RCC dams from the RCC database, some from Vietnam, and then also some from Brazil. Next. Next. Okay, from this, from this database, we found that the average cohesion at lift lines was about 65% of the overall parent strength. So unjointed is on top, and in red, the jointed is on the bottom. Next. This is from Upper Stillwater Dam. The long-term shear strength of these cores had lift lines averaging about 75% of the parent concrete. But we were able to identify hot joints, which are the dotted on the red, and then flat or planar joints, which is below. So the hot joints were the equivalent shear strength of parent RCC. Next. Some of the effects of poor compaction are shown here, where we have all of the lift lines from the database. And then we have lift lines that have voids, generally due to lack of compaction. Voids were 50% less strength than where it was compacted. On this lower one is new information where there was poor compaction on a low cementitious mix. It had virtually zero cohesion, even on intact lift joints. This is another one that shows effect of shear strength on performance. This is a fully compacted RCC mixture for normal stress of 7 MPa, had a shear strength of 3.7 MPa. Next. When there was voids and lack of compaction, at the same normal stress with the same mixture, shear strength was only 30% of the fully compacted strength. The presence of lack of compaction also greatly influences the shear resistance from the sliding friction resistance of RCC, from fully compacted to some small voids, and where there are larger voids and rock pockets, the shear resistance angle was down to 35 degrees. So there is documented poor performance of the low cementitious mixtures when there is no bedding used. This has been shown with more than 50% lift lines not bonded. Segregation was common, and less than 95% compaction was observed at lift lines. One of the primary reasons is the high VB time that is commonly associated with these low cementitious mixtures. The high VB times have segregation, often resulting in low compaction and little or no bond or cohesion. So you must use the proper VB time test and use it properly. Next. The performance of dam facing systems has been evaluated, including formed concrete facing, grout enriched and grout enriched GEVVR facing. And I also talk a little bit about performance of impermeable membranes. But the performance has improved greatly with more workable mixtures, the use of set retarders, and the use of the grout enriched methods. Most dams have had improved overall dam facing performance. Using a variety of methodologies, we're seeing the CVC to the left from Brazil, two types of grout enriched in Africa and in China, and then GEVR and different ones shown here in Vietnam. Next. Contraction joint performance has been very satisfactory. Methods of inducing cracks using vibrating steel sheets and vibrating into thick mill plastic have achieved tolerances of plus or minus 25 millimeters in alignment.
Tim, we can't hear you.
I apologize. I don't know how that happened. This shows performance of attached membranes. It has been excellent with proper installation. There's a little bit of documentation with poor installation. Performance of spray-on membranes has ranged from good to very unsatisfactory. It must have good surface preparations and applications. There's been post-construction grouting of some dams, including arch dams, before filling that has been satisfactory. But when you have flowing cracks that have been filled, urethane injection has commonly been used and has been successful, but only temporary. This shows a barrier cutoff that that was put through perpendicular to a crack. This is an internal steel sheet membrane where it was put down the entire depth of the dam. And this shows, the next slide is before and after performance. Next. This shows a flowing crack, where these cracks were caused because there were not induced cracks in the dam. These are thermal cracks, but the before and after shows that the barrier was very effective, but it was also very costly. Durability performance of RCC includes freezing and thawing, abrasion erosion resistance, and alkali aggregate reaction. Performance in freezing and thawing. Low cementitious mixtures and those without air entrainment have had poor freezing and thawing durability. By using air entrainment, and again, more workable mixtures allow you to get air entrainment, you can get good improved performance. To the upper on the left side is non-air entrained RCC that had very poor performance. And to the lower right, where there is freeze-thaw resistant concrete, you were able to get good performance. Abrasion erosion resistance of RCC. There are some places where there is exposed RCC subject to abrasion erosion. And the principal requirements of conventional concrete and RCC are the same. The higher the compressive strength, the greater the abrasion erosion resistance, and low strength RCC has very poor resistance. There is one documented case where there was a reactive aggregate used with high alkali cement in a temporary diversion structure with a short service life, and that does have documented alkali aggregate reaction. Some of the other unusual or extreme loading conditions, including seismic loading, spillways, and some foundation-related issues. To date, RCC dams have performed satisfactory under seismic events. RCC that has been overtopped, including cofferdams, has been very satisfactory. The Câmara Dam in Brazil had a foundation fault, and there was a failure in the foundation itself, but the dam itself also had some issues. RCC spillway performance has been satisfactory. The one on the left is a formed air-entrained RCC that was overtopped within a year of construction. And the Ochaco Dam spillway plunge pool was operated within 6 months of completion with satisfactory performance. Embankment dams have been have downstream facing with RCC, and to date, the RCC overtopping protection has been very successful. We have to learn. I think the people that we've had here have all shown that we have learned from our mistakes, but we cannot forget those. We must remember that these can happen, and that in order to achieve performance, we must pay attention to the RCC and have good quality all the way throughout. Conclusions: the RCC performance has improved comparable to CVC dams. The improved workability of the RCC has greatly decreased any issues with lift line compaction. VB consistency less than 20 seconds is recommended. High VB consistency mixes have had segregation and low compaction and poor performance. So supplemental bedding mixtures are necessary to achieve satisfactory performance in these with these mixtures. Lift line performance is greatly improved with hot joints and the clean joint treatment methodologies that have been improved in the past years. Next. Lift line and dam facing performance has greatly improved, and set retarding admixtures have greatly assisted in these improvements by having many hot joints. Contraction joint performance is satisfactory, provided good construction methodology is followed. Freezing and thawing durability performance has been greatly improved with air and train admixtures. Abrasion erosion resistance has improved with increased strength. RCC is not resistant to alkali aggregate reaction unless appropriate measures are taken. And many of the mixtures, as we know, have supplementary cementitious materials that improved RCC durability. Thank you.
Thanks, Tim, for being ready to jump in on that. Good work. Hello, and welcome to workshop number 1 on roller compacted concrete dams at the Icold Symposium on Sustainable Development of Dams and River Basins. My name is Michael Rogers, and I'm going to present this session on Bulletin 177 for roller compacted concrete dams, Chapter 8, Other Uses for RCC in Dam Construction. We know that RCC is a very adaptable material, a very adaptable approach to construction of concrete dams. It can be used in many different site locations and can serve many different functions for construction. It has adaptability to material availability, what types of materials are available locally, and the economies of those materials. RCC offers many advantages for construction. Speed or fast placement is high on that list, as well as economics or low cost for construction. But the key to realizing these advantages is really to keep it simple. As you can see from this photograph, this is a very simple construction site. However, concrete is being placed very quickly. If you count them up, there is less than 20 operators and workmen on this site. Yet this was at the time, a world record placement of roller compacted concrete at the Alevinheim Dam in San Diego, California. First, I'm going to start with a classical use of RCC, which is overtopping protection for embankment dams. This type of work really dominated the early uses of RCC in many areas, including the United States. It provided low-cost emergency spillway expansion. As an engineer, I was faced several times with embankment dams that had insufficient spillway capacity. So the dams would be overtopped in very large floods. This was especially prevalent as the design floods increased. The maximum probable maximum floods were increasing, and these design floods were increasing. A methodology had to be developed to allow these embankment dams to be overtopped. RCC was well suited for this approach by providing an armoring to keep those embankment dams from failing, to allow overtopping, and for the dam itself to survive the flood event. This is a typical section of an RCC overtopping protection, showing the existing embankment with the new RCC pads on the downstream side, allowing protection and a toe protection to protect it against scouring. This has a hydraulic, broad-crested weir type hydraulic controls. Overtopping protection is good for extreme floods and is very adaptable, very efficient, very quickly to implement for embankment dams. It allows the embankment dam itself to be used as an auxiliary emergency spillway. It allows protection of embankments or other cofferdams under construction conditions. And there are many instances around the world where this type of overtopping protection has been provided both in permanent works and under construction conditions. RCC can also be covered over for minimal environmental impact. These photos show RCC as it was completed, and then soil and grass placed over the top of that RCC to give it a natural look. Then under flooding conditions, should they occur in emergency conditions, water would overtop and that grass material under high flows would be removed, exposing the RCC that continues to remain and protect the embankment. The RCC offers a flexibility for the spillway type control. The crest itself can be modified for broad crested weir, as I showed in the last picture, but you can also add reinforced concrete on the crest to allow a sharp crested weir or an OG crested weir for whatever hydraulic conditions are required. Now I'd like to show you a specific application of this overtopping protection that was recently used at the Oroville Spillway in 2017 after the large incident and near failure of the spillway structure. During that event, flow over the auxiliary spillway created large amounts of erosion. And so the decision was made to protect that slope of the auxiliary spillway. Shown here is in blue is the roller compacted concrete splash pad. This is an erosion protection measure that was added to protect the spillway or the slope from erosion and act as the emergency spillway. The cross section shows a RCC buttress added to the downstream side of the dam to support the emergency spillway with the RCC splash pad on the downstream side and a cutoff wall, a vertical cutoff wall at the very end to resist erosion and undermining of the splash pad. This is a rough picture of the plan of the RCC protection with the spillway crest along the top with very little OG here and then building to larger and larger gravity spillway sections. And then the RCC with its flexibility allowed us to build two channels, one on the left and one on the right, to bring those overtopping flows downstream. The cross section looks like this. It looks very similar to this overtopping protection you would see on an embankment dam, but it's very, very long, more than 200 meters downstream. And then the thickness and the step nature of the RCC continues. So there's the energy dissipation. And then for this application, we put a large secant pile wall down at the downstream end to protect that toe from undermining and damage to the slope protection under operations. This slide shows the initial construction stages with the secant pile wall had been installed and the initial excavation had been done. The secant pile wall was then backfilled on one side deep with the RCC and then a small protection pad on the left side. On this photo, flow is from right to left. And so you can see the start of this RCC splash pad as the stepped spillway nature of it is being developed. This photo shows progress photos. The photo on the left shows about 30% construction as that RCC was coming up the hill. As you can see, it's typical RCC. It's placed in horizontal lifts, about 30 centimeters, and just brought up and continued to be brought up all the way to the top of the dam. In the foreground are those large gravity spillway structures, and in the background is the smaller OG hydraulic control structures. This brings us to section 8.3 of the RCC bulletin, which addresses buttressing or stabilization of a concrete dam, typically for seismic conditions. And my experience has been in California in the United States. And in that region, we've used RCC for buttress stabilization in two different ways. Buttressing the dam itself, leaning against the existing structure, like the spillway section at Oroville that I just showed you. And a second approach is infilling. Shown here in this photo is an Eastwood type of dam, a multi-barrel arch dam that has hollow buttresses and space in between these buttresses with small arches across the upstream side. Now, this structure was very strong in the upstream and downstream direction for seismic conditions, but very weak in the left and right direction. And so infilling the structure with RCC gave the structure a very strong cross canyon component for resisting seismic forces. Moving on to section 8.4, erosion protection, and I'm going to talk primarily about spillways and stilling basins and armoring downstream of a dam. And this brings RCC back to its roots. The use of rollcrete, as it was called back at Tarbela Dam in Pakistan. More than 900,000 cubic meters of rollcrete was used for the stilling basin that started erosion on initial operations and was creating a threat to the existing dam. So this is one type of application where that material was added to protect the stilling basin from erosion on the downstream. Moving on to foundation replacement. And this is where I've had some recent experiences, again, working in California in the United States. I'm going to start with Olivenheim Dam near San Diego. This is an 100-meter high RCC dam. And on the left abutment of the dam, shown in this area, there was a topographic low area. And the design required that the dam was tall in the main valley and then got shorter, but did not get taller again as it came over to the edges. And so the design looked at this structure called a shaping block. And we did an analysis where the size of that shaping block was brought in and brought in and brought in until the forces along the base of the dam were the same as if it was sitting on a semi-infinite plane of foundation. And so we designed this structure using RCC so that this shaping block here, shown with the carpi membrane on the upstream side for water protection, seepage protection, functioned as part of the foundation. And the dam on top of it functioned as part of the overall dam structure. And so this dam sitting on the foundation reacts as the same sitting on this shaping block as it does sitting on the foundations to the left and to the right of it. Now we come back to Oroville. Oroville started as a problem with the spillway erosion, shown here on the far left, where a large portion of the central part of the spillway failed. And during the operations that continued, more than 1 million cubic meters of material was eroded from this area. So this left a hole, a very large hole, that needed to be filled in order to rebuild the spillway. RCC was the best material that could fulfill this need to replace the foundation. The middle picture shows RCC as it had been used to fill the foundation, the holes in the foundation, coming up out of the bottom and being placed progressively, marching upwards upstream toward the crest of the dam. The photo on the far right shows how that was done. RCC at Oroville, with classic RCC, was placed in horizontal lifts, but then the shape of the slope was formed with a special tool to create a smooth spillway slope. These pictures show some more of the details of RCC for foundation replacement at Oroville. Some of the deep canyons are shown here on the left as the RCC is placed in these horizontal lifts, and then the side slopes are placed on a 1-to-1 slope using this vibrating plate to form the slope so that no forms were needed on the outside. And then the RCC on the right is shown as it's coming up this slope. And the RCC is shown as being very adaptable to fit into these crevices and these openings of the eroded spillway. This picture shows the progression of the RCC. On the left showing early September 2017, and then just 2 weeks later, you can see how far the RCC had gone up. On the picture on the right, these side slopes, these are those 1-to-1 slopes coming up, and then the spillway slope itself is 4-to-1. And all of that is done without special forms for the RCC. This shows a close-up of that 4-to-1 slope coming up with the RCC being placed and then that special tool being placed. In the background, you can see these RCC walls, these training walls that are gravity walls being placed as we go. And those walls are very interesting. They were placed using these Hilfiger walls, like a reinforced earth wall. Again, there's no forms out here. It's just these Hilfiger walls, these reinforced earth walls that are used with the reinforcing nets tied to a steel frame on the outside. And you can see the conventional gravity shape of these walls. And these walls were just built sequentially, moving upstream, higher and higher. A typical wall height was about 5 meters. This shows the construction of that wall. You can see on the left the baskets of these Hilfiger walls being built, filled with RCC. These baskets about 60 centimeters high and being filled up as they went up with the extension of the baskets on the top. These left an exposed steel mesh and reinforcing was added to that, and then shotcrete put over the top of it and made into a very smooth training wall using RCC, again with no hard forms being used, and this allowed very fast placement of RCC and very strong. This is the final finishing of the Oroville Spillway slope on the 4-to-1 slope, and you can see it came out very nice with the slope and then these gravity walls as they were finished. And there's the final Oroville spillway as it was finished with roller compacted concrete. Again, this was RCC placed in horizontal lifts, and then a final 4-to-1 RCC overlay placed over the top of it. And the walls are gravity walls with a shotcrete inside liner for resistance to erosion during spillway operations. Section 8.6 of the bulletin deals with cofferdams. And there's a couple different types of cofferdams that are out there. Integral cofferdams and then those that are detached or standalone cofferdams. The photograph on the right is the cofferdam at the Three Gorges Corporation, provided by the Three Gorges Corporation during construction of the Three Gorges Dam. RCC, when used for cofferdams, has many advantages. It's very strong and stable and durable, especially in overtopping. And it can be built very quickly. The disadvantages, in most cases, it's more expensive than classical rock-fill type cofferdams and can be difficult to remove. But for the case of Three Gorges, this cofferdam was removed using explosives in the water and allowing the materials to be removed or left in place in the water. The Beni Haroun project in Algeria is an example where a cofferdam was used as an integral part of the RCC dam. It was placed first, as shown on the right, as an initial cofferdam, and then while it was providing protection, RCC was added to the foundation behind it and then brought up and above and provided itself as a cofferdam as it went up. A very good use of RCC for both a cofferdam and a final structure. Section 8.7 in this bulletin deals with raising concrete dams. RCC has been used in several projects for raising existing concrete dams. As shown on the right here, a classic example of an existing concrete dam with the new RCC dam buttress on the downstream side and then raising that above the height of the original dam. It is a very economical method of adding additional storage and extending the life of an existing project, while at the same time minimizing environmental impacts versus, say, building a new dam. So this gives you additional storage with very minor environmental impacts. This is an example of the San Vicente Dam construction. And in this photo, you can see the RCC on the downstream side of the dam being added as a buttress to the existing dam. The existing dam, the concrete has been removed. The skin has been removed with high pressure water, exposing the coarse aggregates. And then the RCC is placed up against the downstream side of the dam. And eventually it will be raised higher above the crest of the existing dam. And there's the finished San Vicente Dam in San Diego, California. With that, I'll finish my presentation. Thank you very much for your attention, and I wish you a good day. Thank you.
Good morning again, ladies and gentlemen. My name is Quentin Shaw, and this section of the workshop will be focusing on RCC arch dams, Chapter 9 of Bulletin 177. The structure of the presentation on RCC arch dams will start with a background. I will then move on to provide an illustration of some completed RCC arch dams, and then I will move on to look at an introduction to the different technologies involved in this type of dam engineering, and I'll finish with a short summary. So, Chapter 9 of Bulletin 177 addresses RCC arch dams. There are 70 RCC arch dams in the world. 58 of these are thin arches, and 12 of them are thick arches and arch gravity structures. The highest RCC arch dam completed to date is Wanjiakuzi in China, which is 168 meters in height, and it is a thin arch. Almost 30% of all RCC dams constructed to date in China are RCC arch dams. Of the total number of RCC arch dams currently in existence, 60 are located in China, and another 2 located outside China were designed and constructed using Chinese technology. All of the other RCC arch dams in the world are currently either thick arches or arch gravity structures. The first 2 RCC arch dams were arch gravity structures, and these were constructed in South Africa in the late 1980s. Developing different concepts at the same time, RCC arch technology subsequently accelerated greatly in China in the middle 1990s. So Canalport and Wolverdans dams were constructed in South Africa in the late 1980s. Canalport is 50 meters high, comprising 56,000 cubic meters of total concrete volume, a vertical upstream face and a downstream face inclined at 0.6 to 1, and realistically only requiring arch action for stability under additional safety factors under load. The structure, although a grouting system was included in the structure, it was never actually grouted. Wolverdans, on the other hand, comprises 220,000 cubic meters of total concrete, 70 meters high, vertical upstream face and a downstream face inclined at 0.5 to 1. This structure does arch under normal loading conditions, and consequently a full three-dimensional function was required. A grouting system was included on radial joints, and this grouting system was subsequently grouted in 1992, although subsequent analysis and investigations on this dam after that established that the grouting system didn't need to be grouted, and that what had functioned in the grouting exercise had not really significantly improved the overall structural function. Subsequently, during the 90s and into the 2000s, saw many RCC arch dams completed in China, with the first one being Pudding, which was finished in 1994. And as can be seen from the successive presentation of slides that I will go through now, some interesting arch configurations were constructed in China throughout the subsequent, the intervening period right up until present. So we see Pudding, Wenkangbao and Shapai dams in this slide. As mentioned, realistically, we have some quite thin arches even in relatively wide valleys constructed in China. As is clear in these presentations, so with some quite complex spillway structures constructed into the RCC. Updating through 2009, 2010, some examples, again, some particularly wide valley arch dams. As with most dams in China, quite significant spillway capacities included. Then, moving on to talk about RCC arch dams outside China. The first RCC arch dam completed outside China and South Africa was Changuinola 1, constructed in Panama and completed in 2011. Then Gomulzam, similar time, also completed 2011, and Portuguese dam in Puerto Rico, finished in 2013. And here we have essentially Changuinola 1, constructed with non-Chinese technology, Gomulzam in Pakistan, which was constructed as an arch gravity dam with post-cooling and joint grouting in accordance with Chinese technology and constructed by a Chinese contractor. And Portuguese dam, a thick arch constructed by Regados. And essentially, so the two non-Chinese arches here, slightly different technologies used, but neither of them were grouted. The joints were not grouted in either of these structures. Then we have Namgam 5 dam in Laos, which was again a Chinese technology arch constructed and designed by a Chinese contractor. Kotanli Dam in Turkey, completed in 2015. Arch gravity structure on relatively poor foundation and constructed in the warmer season in a very cold climatic region, and without joint grouting. Then Tabalaut Dam in Algeria, completed in 2015. Tabalaut Dam is essentially a curved gravity dam that relies on arching for additional safety factor, particularly under seismic loading, with a large significant fault located quite close to the dam and accordingly quite severe seismic loading. Then Korulu Dam in Turkey, completed in 2017, again in a relatively severe climatic area where construction could not be undertaken during the winter season, so only an 8-month construction season essentially during the warm period of the year. I'll talk a little bit more about this one under the technology for RCC arches, but in this case, strategic post-cooling was used, so not for the majority of the dam, but just strategically, in addition to joint grouting, strategic joint grouting. Then we have Jani Dam in Lebanon, which will be 165 meters high when completed, and this dam is currently under construction with only first RCC sort of placed to date. Arenal Dam in Honduras is believed to be currently under construction, although information is not freely available on this dam. And then schedules to start in 2022, we have the Gross Dam raising in USA, near Boulder, Colorado, which will involve the raising of an existing curved concrete gravity dam constructed in the 1950s, using an overlay and raising in RCC and converting it into an RCC arch dam. So moving on to talk about the different technologies in RCC arch dams, and the primary technology on which basis most of the RCC arches have been constructed to date, Chinese technology. Now, early systems for the Chinese arch technology involved arrangements in the structure to accommodate higher levels of displacement associated with temperature drop load, to accommodate the fact that grouting of the joints may be delayed or may be less efficient than is typically the case in a conventional mass concrete dam structure. So such things as short joints on the edges and hinge joints in the middle were developed to accommodate this eventuality. And a system of jointing, which they term form joints and induced joints, were applied, whereby the form joint is actually a system installed, precast system installed across the full height of a particular joint. So every single layer would have the installation of a precast element with a grouting system inside. And an induced joint involves a joint where a similar precast system will be installed not in every joint, not in every layer, but in either every second or up to every sixth layer. And these are rigid systems that are essentially installed and anchored into the layer beneath before the RCC is spread. So RCC is spread over these systems and compacted into them and next to them. And grouting is either undertaken in stages with multiple grouting systems or with a re-injectable grouting system. And in recent years, it seems that a greater approach to post-cooling of the RCC and full joint grouting before impoundment has been adopted, much more in a very similar manner to is applied to conventionally vertically constructed mass concrete arch dams. So moving on to other systems for RCC arch dams, other technologies, particular system that was used at Changranola 1, Katanli, Kuruglu, and partly Jane Dam involves installation of a crack directing system to create joints through the creation of a groove in the compacted RCC into which a jointing system is added, and this jointing system can contain a grouting system, or it can be a simple ungrouted system. And the big advantage of this system and this technology is it follows the RCC placement. So basically, it is not on the critical path. All activities occur in the manner of a conventional RCC dam construction. Following that, the system comes behind to create the joints, and in the already compacted RCC, so absolutely no interference at all with the RCC placement. So this system has been applied locally and generally on different dams, with early dams having the entire structure involving this system with grouting across the full joint areas, and more recently strategic areas have been grouted. And in this case, the Kurulu Dam represents a very good example. And as I mentioned, this was constructed in over the 8 warmer months of the year, but had to be designed to accommodate very cold winter conditions. And at this dam, it was found that the low stress relaxation creep behavior of the RCC could be taken into account and taken advantage of to allow a situation where only strategic post-cooling and grouting was required. So if you look at the figure in the center of the presentation here that says area post-cooled, only the light blue area was actually post-cooled. On completion of the dam structure, this area was post-cooled, which happened fairly rapidly, leaving the heat in the base of the structure. And post-cooling and grouting this part before water loading ensured that the ongoing cooling and dissipation of hydration heat of the structure would actually continue to tighten the joints, tilting the structure downstream and tighten the joints, allowing a situation where regrouting of the grouting system would never be required. Now, achievable placement rates are a very important consideration in RCC dam construction. And looking at Malcolm Dunstan's 2015 presentation of average rates of placement of RCC compared to total dam volume, and plotting the arch dams, typical arch dams of different technologies on this, is very interesting to see that achievable RCC placement rates for Chinese technology arches are apparently compromised, whereas the achievable RCC placement rates for RCC arch technologies from outside China are approximately equal to that of an equivalent RCC gravity dam. It's also important to note on that same point that the RCC arches elsewhere outside China have been heavier structures and arch gravity structures where the simplicity has also allowed an acceleration of the construction rates, the achievable construction rates. So it is true to say that Chinese RCC arch technology essentially constructs conventional double curvature arch dams in roller compacted concrete, whereas RCC arch technologies elsewhere tend to construct normal RCC dams with three-dimensional structural function and benefit significantly from the efficiencies associated with low stress relaxation creep RCC. Chinese RCC arch technology is more complex, slower, generally requires post-cooling and more complex spillway structures, but will gain the benefit of between 5 to 20% less RCC than is required for a conventional arch gravity dam configuration. Non-Chinese technology typically requires 5 to 20% more RCC, but can be constructed at normal higher RCC placement rates and can impound water immediately on completion of the structure. Non-Chinese arches do not need to adopt a traditional arch gravity form, although most have to date. That's not really essential, but experience has shown that they tend to be configured for maximum constructional simplicity and speed, and accordingly take on a simpler form. So to summarize, it's interesting to note that almost 30% of all the RCC dams in China are arches, and yet less than 2% of RCC dams elsewhere in the world are arches. Certainly, China has many more suitable arch sites, but there seems to be a general reluctance to use the technology elsewhere, which has only recently started to change, with many RCC arches in the planning phase and currently under design. While RCC will generally be the optimal solution for a gravity dam, assuming design for simplicity, a much more less easily defined line exists between RCC and conventional vibrated mass concrete arches, with vertical construction becoming more efficient than horizontal construction on narrow dam sites with steep abutments, and for several reasons. Consequently, the most obvious place for RCC arch dams is on relatively wider sites, which suit thicker arches or arch gravity configurations, although there is certainly no need to restrict the structural configurations to vertical upstream faces and inclined downstream faces in a conventional arch gravity. So, to gain the full benefits typically associated with RCC, for an RCC arch, simplicity remains the key element and requirement. And the opportunities in RCC arches, particularly taking advantage of low stress relaxation creep, are very significant, and this dam type must always be considered as an option on potentially suitable dam sites. Thank you for your attention, and thank you for the opportunity of being able to present on this subject of RCC arch dams at this workshop.
Hello, Jeng sir. Hello, Jeng sir. Hello,
Hello.
sir. Please start for next PPT for Jeng sir.
So this is the period for questions and answers. So our host, will you be asking questions?
No sir. No sir.
So there's no time for questions?
Yes sir.
I have followed the chat during all the presentations. I have not seen any questions coming from the chat. So if attendees have questions now, there would be the opportunity still to ask either through the chat, or I don't know if it is possible to submit questions directly to the moderator. I'm observing the chat, so let's see what is coming through there.
Hello, please start next presentation.
The presentations are all done now for this workshop.
Yes, sir, but
So-
next 1:30 start for presentation now.
So we don't have any time for discussion.
Yes, sir. Yes, sir.
All right, that's a pity. Anyhow, I thank all the presenters.
No, sir. No, my next presenter is Zhang.
Okay.
Okay. Thank you, gentlemen.
Thank you very much.
Thank you.
Thank you, everybody.
Thanks, sir. Please share your screen.
Hello. Should I begin my presentation? Hello.
Yes, sir. Hello.
Hello.
Yes.
Next is my presentation, right?
Yes, sir. Yes, sir. Yes, sir.
All right.
You can play, please.
Can you see my presentation?
Yes, sir.
Hello.
Yes, sir. Yes,
All
sir.
right. Yeah.
I see the
Good
presentation.
afternoon, ladies and gentlemen. Welcome to my presentation. On behalf of Icold, it's my pleasure to give a brief introduction to RCC technology and some new progress in RCC in China. I'm Zhang Guoxin from Icold. My speech include the following part. The first is an introduction to the development history and achievement of China. Achievement of China's RCC dams. Secondly, I will introduce several famous or important RCC dams in China. Third, I want to talk something, some main features of China's RCC dam in designing, including gravity dams and arch dam and dam seepage prevention. The fourth is the introduction of two new technologies, two new progress in RCC recently in China. Finally, I will make a simple summary. First of all, a brief introduction on China's RCC dam development. In China, the RCC technology has become the most popular concrete dam construction technology because its advantages, such as safety, economy, and speed in the construction. Dr. Dunstan developed an RCC dam database that summarized and analyzed the RCC dams around the world. According to the database, as of 2019, there were about 1,000 RCC dams in the world, all around 5 continents.
होना चाहेगा ठीक है और लास्ट में
Hello?
सीमा पांडे अगर वीडियो प्ले कर देना अपने आप कंक्लूड करेगी अगर वो होना चाह रहे कि पीपीटी है वो है नहीं तो हम पीपीटी रन नहीं कर सकते
Can you hear me? According to Down Standard date, there are 11 countries that have completed more than 10 RCC dams with height of 30 meters. From this chart, we can see China has the most RCC dams, accounting for more than 30% of the world's total one. More than 70 countries around the world are built RCC dams. This picture shows 11 countries with more than 10 RCC dams. As of 2019, there are 780 dams over 30 meters in operation around the world. That amount of them, there are 258 in China. More than in 1986, the first RCC dam, Icold RCC dam, was built in China. Since then, the number of RCC dams has increased rapidly, steadily, year by year. The fastest development in the recent 10 years after 2010. More than 140 dams have been built. By year 2020, a total of 258 RCC dams with a height of more than 30 meters have been put into operation in China. And also, there are many more lower dams with a height of less than 30 meters. At present, and as an estimate, more than 70% of concrete dams with height below 200 meters are constructed using RCC technology. This is a dam height distribution of RCC dam in China. The largest number is 74, which belong to the dam's height range of 50 to 80 meters. There are 65 dams with a height of more than 100 meters. Among them, 2 dams with a height above 200 meters, namely the Guangzhou Dam and Huangdong Dam with height are 200.5 meters and 203 meters, respectively. This is the distribution of 65 higher RCC dams with a height of over 100 meters in China, mainly in the southwest of China. Next, I will introduce a few famous important RCC dams in China. The first one is Puding RCC arch dam. It was built in 1993 and is the first RCC arch dam in China. The dam is 75 meters height, crest length about 200 meters, and 28 meters thickness. It is a single curved gravity arch dam. In the construction of Puding arch dam, a series of RCC technologies has been developed, such as arch dam jointing technology, induced joint, RCC mixture propulsion, growth-enriched RCC, impacting technique, etc. Provided basic technology for the construction of a large number of RCC dams in China later. The second is Shapai RCC arch dam. This dam was with a height of 132 meters and was completed in 2001 year. It is the first RCC arch dam with a height over 100 meters in China. A series of technologies are applied in this dam, including the thermal load and temperature control technology for arch dam, the water cooling technology using plastic pipe, the repeat grouting technology of the transverse joint and reduced joint, etc. At the Wenchuan earthquake occurred in 2008, the dam is only 36 kilometers from the center of the earthquake. And the earthquake intensity in the dam site is over 9 degrees. That means the dam experienced a heavy earthquake and have no damage and kept intact. The Shanghai Arch Dam won the International RCC Arch Dam Milestone Award in 2015. The fifth one is, the fourth one was to introduce this Guangzhou RCC gravity dam. The height is 205.5 meters and was built in 2008. It was the first RCC dam over 200 meters and also the highest gravity dam at that time in China, higher than the Three Gorges Dam, and also the world's highest RCC gravity dam in that time. In 2012, Guangzhou Dam won the International RCC Dam Milestone Award. The next one is Fengman RCC gravity dam, not so high, with a height of 94.5 meters. It was completed in 2018. The biggest feature of this dam is the location in a very cold region. The lowest temperature recorded in the dam was minus 45 degrees centigrade, and the maximum annual temperature difference was 80 degrees centigrade. During the construction of the dam, we developed temperature control technology for mass concrete in several cold areas, concrete anti-cracking technology during the cold season, and the combination technology of new and old concrete after the winter, RCC concrete surface protecting technology, and also RCC intelligent temperature control technology, etc. The next one is called Wanjiakou Arch Dam with a height of 167 meters high. Was built in 2019 and is currently the highest RCC double curved arch dam in China. The Huangdong RCC gravity dam is 203 meters high and was completed in 2018. It is currently the highest RCC dam in China and also the highest gravity dam in China, with the installed hydropower capacity of 1.9 gigawatt. During the construction of this dam, the RCC Dam Intelligent Construction System was developed and successfully applied, including the raw material quality control, construction quality control system, RCC Intelligent Rolling System, and Intelligent Temperature Control System. The third part of my presentation is a brief introduction to the main features of the RCC dam in China. The first is a gravity dam. China has built more than 258 RCC dams with a height of more than 30 meters, of which 186 are gravity dams, account for 72%, and 72 arch dams account for 28%. Then I will introduce the main features from three aspects: cross-section design, dam material zoning, and contraction joint spacing. For the cross-section of the gravity dam, according to Chinese standard, the cross-section design of a gravity dam must meet two conditions. The first is no tensile stress, and the second is the anti-sliding stability condition that requires the safety factor K of anti-sliding stability along the dam foundation, and any horizontal plane against the water thrust should be greater than 3.0. RCC dams have roller compact layers and lift joint. It is generally considered that the interlayer shear strength is lower than that of the conventional concrete. Therefore, the interlayer shear resistance may be the controlling factor for the sections designing. During the design of long-term RCC dam, the interlayer shear strength is given through a lot of experiment. That is, the friction coefficient of equal 1.07 and C equal with 1.97. We have accounted the result of on-site concrete shear test or core shear test of more than 10 projects. Because we can see this table. The shear parameters. The range of friction coefficient is about 1 to 2, and the average value is 1.33. The cohesion strength range is 0.9 to 4, with the average value is 1.73. The downstream slope of the is between 0.68 to 0.8, with the average value of 0.73. Several dams with a height of about 200 meters, such as Longtan, is 0.73, while Guangzhou, Huangdeng, and Jinanjiao are all 0.75. In the cross section of dam, we use different concrete zones. In the early RCC gravity dam in China, we used two zones. CVC was used near the upstream and downstream surface of the dam as protection, and RCC was used inside the dam. That is called gold and silver. But in the practical, we have found that this way will increase the difficulty of construction, and also the surface concrete is easy cracking. Therefore, Chinese RCC dam currently adopt the full section RCC, but different grade of RCC are required considering the stress distribution and the function of different parts. For example, the Longtan RCC dam adopt 5 zones. As shown in the picture, 2-grade RCC concrete is used near the upstream part, and the 3-grade RCC is used inside. The lower high stress area use higher strength and impermeable RCC, and the upper low stress area adapt the low strength RCC. Conventional concrete is used near the downstream surface. For design age of RCC, in the early years we use 90 days, but now we use 180 days as design age. Contraction joint in gravity dam are designed to reduce thermal stress of the dam axle and to avoid cracks. That is a measure to control temperature and prevent cracking. RCC use less cement and with low hydration heat, it is used to think for RCC dam crack prevention measures can be greatly simplified. Because joint of RCC dam affect the large scale concrete compaction, therefore reduce the advantage of RCC. So in early years, fewer joints or no joints are recommended for RCC dam. RCC gravity dam built in earlier years in China used large joint spacing or even no joint. The distance between transverse joints was up to 70 to 90 meters or even 120 to 150 meters along dam, no joint. But we experienced serious cracks in the project. This figure shows the variation of contraction joint spacing over time for RCC gravity dam in China. In the early years, some transverse joint spacing could reach 100 meters or even some dams without joint. Around the year of 2000, there were still dams with joint spacing of 90 to 80 meters. The maximum joint spacing of dam built in the recent 10 years was less than 40 meters, with space mostly 20 to 25 meters. Some special dam monoliths can be extended to 35 to 40 meters. Water diversion holes, flood discharge facilities, and other layout requirements, but need to take appropriate temperature control measures. All of the China's RCC gravity dams do not have longitudinal joints, although the bottom width of the 200 meters higher dam has reached 140 to 160 meters. Let's turn to the main features of RCC arch dams in China. China built the first RCC arch dam in 1993. Up to now, totally 60 RCC arch dams have been built. Among them, 1995 to 2013 was a period of rapid development because of the advantage of small size and higher safety. Arch dams are given priority in all suitable sites. The first RCC arch dam in China is Puding Arch Dam. It is the single curved gravity arch dam with a thickness to height ratio of 0.37. With the progress of technology, double curved thin arch dam is gradually adopted. For example, the thinnest RCC arch dam in China is Icold Arch Dam with a height of 122 meters. A thickness to height ratio is only 0.15. At present, the shape of RCC arch dams is no difference from that of conventional concrete dam. In the selection of arch dam shape, an automatic optimization method is used. In 1990, academician Bo Zhu and Professor Jia Jinsheng proposed a multi-objective optimization method for arch dam shape designing and developed the optimization software ADASO. The software takes the dam value, overall safety, and stress distribution as optimization target. After optimization calculation, the optimal arch dam shape can be automatically selected. The arch dam built in our country after 1990s are all designed in this way. Joint spacing. We have two kinds of joints, transverse joints and induced joints. The joints of at dam is to release the temperature, stress, and prevent cracks. Starting from the pudding at dam, China used jointing form of transverse joint plus induced joint. Pudding dam adopt one transverse joint plus two induced joints. The largest joint space was 81 meters. Consider the induced joint. The spacing is about 50 meters. At present, China's highest RCC at dam, basically adopt the joint form of two transverse joints plus multiple induced joints, and the joint spacing is generally 40 to 50 meters. For example, the Xiangbiling at dam has a height of 141.5 meters high and a dam crest length of 460 meters. There are two transverse joints and 6 induced joints. 8 dam monoliths have a joint spacing of 41 to 47 meters, and the middle monolith has a width of 74 meters. The transverse joints are connected joints that run through the upstream and downstream and the top to the bottom of the dam. We were continuously placed prefabricated blocks forming transverse joints. Induced joints are partially broken and connected joints formed by spatial placed prefabricated blocks and local vibration cutting. The prefabricated blocks are connected by grouting pipes, and that can be grout repeatedly to form a grouting system. For conventional concrete at dam, we use pipe cooling, especially the later cooling, to make the dam temperature drop to steady state and then perform joint grouting. But for RCC at dam, we usually do not perform the later pipe cooling. The joints are grouted before water storage. After grouting, the temperature of the dam body will slowly drop to a neutral state. As a result, the grouted joint may reopen again. So, repeat grouting is required for the reopened joint. China's in the construction practice of RCC dams in China, there have been many cases of serious leakage. So, in the design and the construction of RCC dam, seepage prevention is an important task. For early RCC dam, conventional concrete layer about 3 meters was used as anti-seepage body in dam on the upstream. Due to the problem such as poor bonding between RCC and normal concrete and complex construction, China's engineer invented anti-seepage structure combined with grout-enriched RCC. plus 2-grade RCC. That is, the main body of the dam is 3-grade RCC. And a layer of rich cementing 2-grade RCC is set upstream of the 3-grade RCC, the thickness of which is a 115 to 120 of the dam height, and in the upstream of the 2-grade RCC, a 50 cent to 150 cent GE RCC layer is added. Since 1993, all RCC dams have adopted this combined anti-seepage structure in the upstream area. The so-called GE-RCC is grout-enriched vibrated RCC. The concept is to add cement grout in the placed RCC. It will be able to be vibrated to achieve a rich concrete of better quality and higher impermeability. Modifies fresh placed RCC in situ to conventional vibratable concrete. The first use of GE-RCC is on upstream phase as anti-seepage layer, but now it can be used in various places such as downstream surface and upstream surface, foundation interface, facing or galleries walls, and spillway, etc. And the GE-RCC has many advantages. No special mixing or transport plant, just adding some pumps to ordinary RCC. Substantially, in order to further improve the anti-seepage performance, a new form of anti-seepage has been developed in recent years. A layer of plastic or flexible anti-seepage paint is applied to the upstream surface of the dam body, such as the upstream of Ludila RCC dam, coated with a layer of 1 to 2 millimeters thick special film, which could repair the surface cracks and play a good anti-seepage effect. Next is an introduction to a new technology, the intelligent construction technology of RCC dam developed in China in recent years, including intelligent rolling or intelligent compacting and intelligent temperature control. The key to the quality control of RCC is the interlayer bonding. If the interlayer bonding is not good, the RCC will become a layer cake, generally reducing the shear resistance of RCC dam, causing interlayer leakage and affecting the safety of dam. There are many examples of serious leakage in RCC dam in China, most of which are caused by poor interlayer bonding. This is an example of a poor interlayer bonding. It can be seen that the drill core is easily broken, and there's an obvious weak surface, every 30 centimeters. There are also examples of dam collapse caused by concrete quality problem and interlayer bonding problem in the world. We developed a smart construction and digital dam management system and used in dam construction. Control all the procedures such as control a raw material, proportion of concrete, placing parallel to initial set, compacting, temperature control. There are several aspects to control the compacting quality. First, the number of rolling times. Second, the thickness of paving layers. Third, the dropping speed. Fourth, the vibration force, etc. The traditional method is to control all kinds of equipment manually. The quality of compacting depends on the technical proficiency and working state of the operator, it is inevitable that there will be problems such as missing compacting, over compacting, missing vibration and over layer thickness, etc. Intelligent compacting based on the higher precision Beidou positioning and navigation system, and GPS, Internet of Things, cloud computing, image recognition, big data mining, and other technologies. It established real-time, intelligent, full process, and efficient RCC quality monitoring system to monitor rolling times, compaction thickness, vibration force, drive speed, and interval time. Compacting thickness, vibration force, and driving and internal time. Effectively ensure the quality of dam construction and provide important means for dynamic construction management. The technical composition includes hardware equipment, analysis model, and software systems. A set of intelligent compacting equipment has been adopted, including compacting machine monitoring terminal, GPS reference station, field sub-control station, and general control center. The main technology is to install various sensors on the vibration compacting equipment, such as DBS locator, GPS locator, vibrator, vibrometer, speed meter, etc., to record and monitor the number of rolling times, vibration force, and walking speed in real time. All mathematical model is established for real-time monitoring of the compacting quality. As intelligent compacting software system is developed to realize the real-time monitoring of the construction with process of monitoring, analysis, feedback, processing. It can real-time monitor the concrete laying thickness, strip rolling time, time interval between layers, and other compacting parameters, alarm the quality risk in time, and real-time analyze the exposure time of concrete layer, direct operation to avoid cold rise. The technology has been successfully applied in Huangdeng Dam, Fengman Dam, and get a good result. The core sample length of Fengman grade 3 concrete reaches 23.18 meters, which is a world record, indicating the excellent quality of concrete compacting. And next one is intelligent temperature control. RCC use less cement, lower hydration heat, can greatly simplify the temperature control. Therefore, in the early years, it was considered that temperature control measures is not needed for RCC dam. However, China's practice shows that if the temperature is not controlled appropriately, serious cracks will also occur in RCC dams. China has formed our own RCC temperature control theory, standards, and measures, such as in low temperature season using surface insulation. In higher temperature season, use spray cooling and pipe cooling, plastic water pipe in water pipe cooling, etc. In recent years, intelligent temperature control technology has been developed. What is intelligent temperature control? It combines information technology, digital technology, Internet of Things, GPS, automatic control, artificial intelligence, with traditional temperature control measures to realize automatic and intelligent temperature control. As we know, the temperature control of concrete includes 4 periods. First is the concrete mixing by wind cooling and adding ice lower the mixture temperature. A second, placement period by cool water spray to prevent the temperature rise. And third, pipe cooling, fourth, surface heat isolation. By the whole process, temperature control realizes the temperature target. Our intelligent temperature control mainly include RCC placing and pipe cooling period. Intelligence degree, we set some sensor to monitor solar radiation, temperature, humidity, wind speed, temperature of fresh concrete, etc. Analyzing the microclimate required for concrete temperature target. Automatically regulate amount of spray fog, intensity, and direction, realize intelligent control of RCC placing environment. And smart pipe cooling through the concrete internal temperature, surface temperature, cooling water temperature, prediction and analysis of the future temperature, automatically control the layer, the water flow in pipe cooling in real time. Intelligent construction management software of RCC dam is developed, which realizes the automatic acquisition and efficient management of construction information, the evaluation of construction quality, the early warning of quality risk, the decision-making support, and intervention feedback of construction measures, and the prediction, optimization, and control of the whole process. And let's go to the concluding remarks. RCC is an excellent dam construction technology with economic advantages, simple and efficient in construction and safety. It has been rapidly developed in China since 1984, and it is currently the main technology used for construction of concrete dam. With 70% of new concrete dams with using the technology, especially the high dams. China has developed a series of innovative technologies in the construction of RCC dam, such as joint making, GERCC, inclined layer compacting, water cooling of plastic water pipe, multiple mixture technology, intelligent temperature control and crack prevention, intelligent compacting, information-based quality control, and other technology. Operation management of RCC dam will be an important task for dam engineers in the future. The RCC dam constructed in the earlier years has been in operation for more than 30 years. Some problems, such as leakage, have been fully exposed, but some problems have not been fully exposed. For example, the temperature of dam body of higher and thick dam has not reached to the last stage, and the temperature will drop gradually, and the stress will increase year by year with decrease of temperature, and new cracks may occur later. There are fewer and fewer suitable sites for dam construction in China, and the construction condition of new dams are getting worse and worse. There are still some technical difficulties to be overcome, and technical innovation is needed. That's my presentation. Thank you very much for your attention. Hello.
हेलो
Hello.
हाँ जी सर यस सर
I finished my presentation.
ओके सर ओके हेलो सुनील सर
Hello,
हेलो
sir. You can play your presentation. Yeah, I will play.
now I'll share my screen from here
Okay, okay, sir. You please share your screen. I stop my screen.
आ जाओ यार क्या हो गया आगे ये छोटा क्यों आ रहा है फुल स्क्रीन करना फुल स्क्रीन फुल स्क्रीन स्लाइड शो करो सर उधर में फुल स्क्रीन वो आ जाएगा Good afternoon to all delegates and participants who are connected with this technical workshop on roller compacted concrete dams. My name is Sudhir Kumar Yadav, General Manager Civil from NHPC. Presently, I am posted at Tista Low Dam 4 power station in West Bengal. Today, my topic of presentation is a case study of Tista Low Dam Stage 4 dam, which is a concrete gravity dam of 45-meter high. For preparing this paper and presentation, two of my colleagues have contributed as co-authors. The colleague Shri BNS Naveen Kumar, Senior Manager Geology from NHPC Corporate Office Faridabad, and another colleague is Shri Vinod Kumar Chaudhary, Senior Manager Civil NHPC, and posted at Tista Low Dam 3 power station, and he is associated with me in this live session. Now, with the permission of chair, I start my presentation. Actually, what is roller compacted concrete? Roller compacted concrete or RCC is a special blend of concrete that has essentially the same ingredients as conventional concrete, but in different ratios and increasingly with partial substitution of fly ash for Portland cement. Roller compacted concrete is a mixture of cement, fly ash, water, sand, aggregate, and common additives, but contains much less water. The produced mix is drier and essentially has no slump. During the hydration process of cement, lime is released out and remain as surplus in the hydrated cement. If fly ash is available in the mix, this surplus lime becomes the source of pozzolanic reaction with fly ash and form additional calcium silicate hydrate gel having similar binding properties in concrete as those produced by hydration of cement paste. The reaction of fly ash with surplus lime continues as long as lime is present in the pores of liquid cement paste. As I said, the RCC is a drier mix and has no slump value. Roller compacted concrete is placed in a manner similar to pavements in thin layers. Material is delivered by dump trucks or conveyors, spread by small bulldozers, and then compacted by vibratory rollers. These are few initial dams where RCC technology was adopted and tested for first time. First is 174-meter tall Alpegara Dam in Italy, constructed between 1958 to 64. In this dam, concrete was poured in layers with a lean mix and settled with immersion vibrators. In this way, this concrete was not only cost saving but instrumental in the development of roller compacted concrete in dam construction. The second diagram is the first RCC dam in USA, the Willow Creek Dam, constructed between 1981 to 83. On initial filling, the leakage between the compacted layers within the dam body was unusually high. This condition was treated by traditional remedial grouting at later stage. The third is Shimaji-Gawa Dam, constructed in Japan in 1980. This was the first dam where complete roller compacted concrete technology was adopted. Roller compacted concrete, these initial dams were instrumental in the development of RCC technology in dam construction. Nowadays, RCC has become very popular due to various advantages associated with it. The biggest benefit of a roller compacted concrete is its speed of construction, because the concrete is laid in layers in continuous process and without much use of formworks and mechanical tools. RCC is durable and it can withstand the repetitive loads and can achieve sufficient load carrying capacity quickly. Low maintenance and cost effective. We can save up to 25 to 30% in cost if we compare it with conventional concrete. RCC is sustainable and environment friendly, as we use fly ash as supplemented as cementitious material, which reduce the amount of Portland cement and thus lowering the embodied energy of a roller compacted concrete mix. Other advantages are RCC is safer against erosion. Due to layer by layer placement, formwork cost is lower. After placement, cooling is not required. Cost of transportation, placement, and compaction of concrete is lower because concrete can be hauled by dump trucks, spread by bulldozers, and compacted by vibratory rollers. It is low permeable, more durable, and simple equipments are used in RCC construction technology. Although RCC has various advantages associated with it, however, this technology is quite challenging. The journey is not easy sailing in construction of RCC dams. The concrete used is essentially dry and maturity time is prolonged for successive lifts. The placement of RCC in successive layers of 300 mm thick is quite challenging. The setting time of RCC depends upon various factors like climatic temperature, concrete temperature, weather, quality of mix, quality of compaction, and quality of workmanship. Thus, control over such parameters is quite challenging. The first two large RCC gravity dams in the US experienced seepage through lift joints and at shrinkage cracks. Thus, a qualitative approach for construction of RCC dams is essential and an important tool for success. Availability of construction material, especially fly ash, in huge quantity is a matter of concern. As far as construction of roller compacted concrete dams in Indian context is concerned, the first RCC dam in India was built in 2006 in Ghadgar Pump Storage Scheme project. Second RCC dam in India is Middle Vetarna Dam. It is also constructed in Maharashtra and completed in 2012. The third RCC dam in India is Tista Low Dam Stage 4 Dam, constructed in Darjeeling district of West Bengal and completed in 2016. Regarding Tista Low Dam 4 project, it is a run-of-the-river scheme project with installed capacity of 160 megawatt, having 4 units of 40 megawatt each housed in a dam to surface powerhouse. The main dam is a combination of conventional and a roller compacted concrete dam. The 5 non-overflow blocks, 4 power intake blocks, 1 number division block and 7 number spillway blocks are constructed in conventional concrete gravity method, and 9 non-overflow blocks on the right bank are constructed with a roller compacted concrete having a length of 205 meter. So the overall length of this dam is 530 meter. The RCC dam also offers a fish pass, as we can see in this photograph, at downstream face, negotiating a gradient of 1 in 11 slope for enabling fish migration. This is location and general layout plan of TLDP4 hydroelectric project. The project is located in Darjeeling district, West Bengal, and very near to Sikkim border. In layout plan, we can see the right bank blocks are of roller compacted concrete, and rest of the dam is conventional concrete gravity dam. These are few salient features of this project. Dam is concrete gravity and RCC. Total length is 530 meter. The height of the dam is 45 meter from the deepest foundation level. Gross storage is 36.63 MCM, live storage 7.91 MCM, installed capacity 160 megawatt, and annual energy generation is 720 million units. Tista Valley, where this project is located, provides a very short working season of about 7.5 months from 1st October to 15th May. It was therefore necessary to divert the river from work areas in phases. Accordingly, 2-stage diversion was planned and executed for the completion of this project. During stage 1 diversion, a channel was provided on the right bank of the river and the river diverted through this channel. The construction of spillway blocks, cellular wall, left bank non-overflow blocks, power dam, powerhouse, and tail race channel on left side of this channel was taken up in this phase and completed, as we can see in this photograph. During second stage diversion, as closure of right bank at location of first stage diversion channel was last activity before commissioning of the project, and time available was only 6 to 7 months before monsoon. Therefore, RCC dam was envisaged as suitable alternative due to its faster construction technology and abundance of fly ash available in the project vicinity. The river was re-diverted to flow over completed spillways, and right bank was isolated for construction of RCC dam. As we can see in this photograph, the river is flowing through spillways on other side of this dike, and right bank is isolated for construction of RCC dam, and excavation activities are going on for the RCC dam. The design methodology of RCC gravity dams are almost similar to conventional concrete gravity dams. However, certain specific parameters are required to be addressed and adopted for the design of RCC dams. For this TLDP4 dam, upstream slope of 0.4 horizontal is to 1 vertical and downstream slope of 0.8 horizontal is to 1 vertical with steps on both sides was considered, keeping in view of geological conditions. high seismic peak ground acceleration, and to take care of the permeability and shear strength requirement at the lift beddings. Detailed dynamic analysis using finite element software SAP and heat rise studies using software ANSYS were carried out to compute the compressive, tensile, and thermal stresses during detailed design. Contraction joint spacing of 25 meter was adopted. It considered adequate to avoid thermal cracking. The design compressive strength of 15 MPa at 180 days was selected based on the level of strength necessary to satisfy compressive, tensile, and bond strength requirement as well as durability. High-paced RCC with cementitious material content more than 200 kg per meter cube was proposed to be used for better performance in the seismically active area, requirement of assured shear and tensile strength, and impermeability of dam. The in situ impermeability of the dam at lift joints was considered as less than 2 lugans. High-paced RCC mix with smaller MSA, maximum up to 50 mm, was envisaged to ensure good bonding between the lifts and to avoid problem of segregation. The month-wise ambient temperature at site varies from 15 degrees Celsius in January to 25 degrees Celsius in April. Therefore, pre-cooling of aggregates and addition of ice flakes to water were envisaged for controlling the placement temperature between 7 degrees Celsius to maximum 15 degrees Celsius depending upon the placement months. The maximum temperature rise within the dam body, considering these placement temperatures, the total temperature in the body was envisaged about 35.29 degrees Celsius. Therefore, maximum volume of RCC placement was planned in cooler months of the year. High content of fly ash and relatively low cement content in cementitious material envisaged for reduction in the heat of hydration. About 60% Portland cement was replaced with fly ash during design mix for this RCC dam. BASF and MCV make chemical admixtures were used as set retarders to delay the initial setting time of RCC. Horizontal joint treatment was planned in a detailed manner and same was confirmed during full-scale trials in the field. This is the typical cross-section of this RCC dam. We can see steps on both sides of the dam. These 90 centimeter steps were provided for supporting the formwork along the progressive height of the dam. A foundation gallery has also been provided to perform curtain grouting and pressure relief holes during construction stage and for inspection during operation stage. Adjacent to this cross section, there is a graph showing maximum placement temperature of the RCC with respect to contraction joint spacing. We can see for 25 meter contraction joint spacing as we adopted in this dam, the maximum placement temperature should be 16 to 17.5 degrees Celsius with a factor of safety of 1.5 to 1.25. However, to be more conservative, in this dam, maximum placement temperature was restricted up to 15 degrees Celsius. And next is concrete volume per lift along the elevation of the dam. So this dam was planned and executed keeping in view the economics, time constraint, and special design criteria. Appropriate mix design for an RCC dam is the essence of success of any RCC dam. In TLDP4 dam, 3 types of cement, OPC Pendon, OPC Shadabdi, and Portland slag cement of Pendon were tested and selected for design mix. The fly ash was tested and confirmed for usage from the identified source and transported in bulk tankers to the site. Hand-picked boulders were collected from nearby identified riverbeds and crushed and planted near dam site for coarse and fine aggregates which were used after confirmatory testing. In order to obtain RCC having suitable workability, consistency, impermeability, strength, and durability without use of excessive cementitious material, mixed proportions for RCC were started within a stipulated range as shown in this table. Mixed proportions of various ingredients were decided considering results of tests within this stipulated range. Further, the final determined mix design was tested in full-scale trials and finalized thereafter. So the final mix design for this dam designed as with nominal maximum size of aggregate 50 mm, free water 126 kg per meter cube, Portland cement 43 grade 85 kg, and fly ash 135 kg per meter cube, and VB time considered for this mix 10 to 18 seconds, initial setting time 18 to 24 hours, and final setting time 30 to 45 with a water cement ratio of 0.57. So we can see that in this mix design we have provided 220 kg cementitious material. These are some quality control tests which were performed for arriving at appropriate RCC mix design. Before placing roller compacted concrete into main dam, full-scale trials were carried out in vicinity of main dam to have a better exposure and experience beforehand. For full-scale trials, a block of 50 meter length by 10 meter wide was prepared and RCC was placed in lifts of 300 mm up to 3 layers for trials by carrying out various activities like formwork, dumping, spreading, and compaction. The trial block was further divided into 4 sub-blocks of 25 by 5 meter for carrying out elaborate joint treatment for hot, warm, cold, and super cold joints. After completion of full-scale trials, the important learnings were proper training and exposure to persons and staff, practice of transportation, dumping, spreading, and compaction of RCC layers, rectification in concrete by changing the composition of admixtures, exposure to various horizontal joint treatments, training for creating contraction joints by installing 2 mm thick and 200 mm deep GI sheet, exposure to GEVR, formwork, curing, etc. Here the term GEVR stands for ground enriched vibratable RCC. GEVR is generally provided in width of 0.5 meter along the faces of the formwork and where dam abuts into the bedrock. In this technique, the desired area is divided into fresh RCC bunds, as we can see in last 2 photographs, and these bunds are filled with additional cement ground paste. Then fresh RCC is laid over these bunds and vibrated by needle vibrators to have a finished and better aesthetic looking surface. These are few more photographs of full-scale trial. We can see spreading of concrete, compaction of concrete, surface treatment, and the final finished layer of RCC. This is batching plant arrangement for main RCC dam. 3 Siemens batching plant of 120 cubic meter per hour capacity were provided for placement for production of RCC for this dam. 3000 cubic meter capacity silos were provided with a storage of 7 days storage for cement and fly ash and to feed these batching plants. This is the arrangement of conveyor system. The conveyor was provided from batching plants to the main body of the RCC dam, and these conveyors were shifted with the help of tower cranes on upstream and downstream faces of the dam. And these conveyors were shifted as per the requirement of placement along the progressive height of the RCC dam. This is a list of equipments that were deployed for construction of this roller compacted concrete dam. This list includes all the important and essential equipments: batching plant, concrete conveyor, vibratory rollers, and so on. This is arrangement of formwork provided for upstream and downstream faces of the dam. 3 sets of formworks were used both for upstream and downstream faces. We can see in stage 4 the shuttering and the formwork provided in stage 1 was removed and provided in stage 4, and similarly in stage 6 the formwork removed from stage 2 and provided in stage 6, and similar methodology was adopted for downstream formwork. This is foundation condition of the RCC dam area after completion of excavation. The rock profiles were undulatory and irregular. RCC portion of the dam was occupied predominantly by slightly to fresh, medium strong to strong sandstone with presence of numerous coal seams and intermittent weak to medium strong carbonaceous shale bands of varying thickness. The coal seams were suitably treated by dental excavation and backfilled with dental concrete. In order to have uninterrupted placement of RCC, the foundation preparation was taken up in very advanced stage. The exposed bedrock was consolidated with cement consolidation grouting, and later on curtain grouting was also carried out through dam gallery. Various instruments like thermocouples, stress strain meters, two borehole point extensometers, etc. have been provided for monitoring the stability of the foundation. For placing concrete in main RCC dam, the conveyor arrangement was made to transport the concrete mix from batching plant to main dam. The conveyor delivery hopper From conveyor delivery hoppers, dump trucks were deployed for collecting and transporting the concrete mix further to the main dam body. The bulldozers were used to spread the RCC. The dozers were equipped with laser-aided leveling sensors so that RCC could be spread in layers of 300 mm. After spreading of concrete, 10-ton single drum vibratory roller was used for open areas, and 2.5-ton small vibratory roller was used near the dam faces to compact the concrete. 60 kg hand-guided power tampers were used adjacent to upstream and downstream formwork areas. In situ density of the compacted RCC was determined by a nuclear densityometer, and this measurement was taken at 10 by 10 grid on the dam surface, and density was measured at two depths of 150 mm and 300 mm on each lift was recorded. Chemical admixtures were used to delay the initial setting time of RCC. Horizontal lift joint like hot joint, warm joint, cold and super cold joints was carried out as tried and confirmed during full-scale trials. The temperature rise in the concrete was planned to be monitored and recorded for a minimum period of 30 to 40 days with the help of thermocouples. Horizontal joint treatment in RCC plays a very important role. Since RCC is laid in layers, multiple horizontal joint lifts are created, which may be classified as hot joints, warm joints, cold joints, and super cold joints. To determine the strength of concrete, maturity of concrete is measured, which is summation of product of age and curing temperature. When maturity factor is up to 400, then we call it as a hot joint. And if a maturity factor lies 400 to 600, then we call it early warm, 600 to 800 late warm, 800 to 1600 cold, and more than 1600 super cold joint. Hot joint treatment was carried out by means of removing all loose material, pool of water or other foreign matter by blowing off carefully with compressed air and cleaning with a vacuum truck. In warm joint treatment, warm joint was clarified with a road brush roller having nylon tins for early warm and steel tins for late warm joint to produce a rough surface. The surface was then cleaned with vacuum trucks. Cold joint treatment, the surface of all cold joints were treated to expose the surface aggregate. For early cold joint, the surface was treated by brooming and low pressure washing, and for late cold joint was treated with high pressure hydroblasting with a pressure of 40 MPa. Super cold joints, the surface of these joints was treated as for cold joint, and cement paste having target water cement ratio of 0.6 was applied on the exposed surface before laying the next lift. For construction of this dam, the whole dam was split into 8 zones, as we can see in this diagram. Maximum 50,000 cubic meter concrete was placed in zone 1 and minimum 8,110 cubic meter concrete are placed in zone 6, and overall placement of concrete in all these zones is 1.68 lakh cubic meter. There are some underlying benefits of split zoning method. Because parallel gallery formwork activities can proceed with no interruption to RCC being placed in another zone. Parallel green cutting activities can proceed with no interruption to RCC being placed in another zone. Efficient utility of construction equipments, better quality control, efficient turnaround of upstream and downstream formworks, more layer per placement per day can be achieved. Hot joint condition between layers can be assured, leading not to treat the RCC surface before starting next fresh layer. Dumping, spreading and getting full compaction can be kept within initial and final setting times. Optimum production capacity from RCC batch plant and conveyance can be consistently achieved. In this TLDP4 dam, 50,000 cubic meter RCC was laid in 50 days, including formwork in zone 1 at a daily average rate of 1000 cubic meter. The remaining 1.18 lakh cubic meter RCC was laid in 130 days. The highest and average pouring of RCC was 1750 cubic meter and 950 cubic meter respectively This is a photograph showing various activities going on main RCC dam. We can see upstream and downstream formwork for the gallery passing through the dam body, conveyor coming to the dam body, and compaction of layers is going on. These are some few more photographs. Gallery arrangement at initial level of the dam, GEVR around rock abutment, and splitting of dam in various zones can be seen in these photographs. Elaborate instrumentation have been provided in this dam for its proper monitoring and monitoring its behavior. The list of instruments includes thermocouples, pore pressure gauges, lift measuring standpipes, strain meter, stress meter, no stress strain meters, inverted pendulum, direct pendulum, perimetric joint meters, survey certs with base plates, 2-point borehole extensiometers, both of electrical and mechanical type. So at the end, I can conclude that good dedicated quality control team is a sense of success of RCC along with well monitored instrumentation, especially for temperature control of concrete during construction. The RCC dam is first of its kind in NHPC and completed successfully by placing 1.68 lakh meter cube concrete in 180 days with average daily pouring of 950 meter cube and average monthly of approximately 28,000 meter cube, including foundation treatment, lift joint treatment, and placement zoning. 3 dams were constructed with RCC technology in India so far, and latest one being Tista Low Dam Stage 4 Dam. The lessons learned from this technology, it would be prudent to adopt more such roller compacted concrete dams in India, especially for sustainable, cost economic in the field of irrigation, as well as hydropower projects, where huge quantity of concrete to be placed at fast construction. Thank you very much for the kind attention. बंद कर स्क्रीन बंद करो वहां से तो बंद हो गया इधर से कहीं से शेयर बंद करते हैं ना हाँ ये शुरू हो गया अगला शुरू हो गया कर दो सर हाँ लीव कर दो हाँ लीव कर
The name of the envisaged dam is Punasanchuvan Dam, which is under construction in Bhutan, was hit by a high flood at the project site. The ongoing works were hampered, and so the diversion arrangements were revised. This led to additional time and cost implication. In order to retrieve the part of the delay caused due to revision of the diversion arrangements, it was decided to construct the lower 65 meter of dam by RCC. The total height of the dam was 130 meters, and it was decided to construct the lower 65 meter of the dam by RCC method. This method would give a faster placement rate, and the cost of the dam by RCC was comparable with that of the CVC. Site characteristics. The slopes on the right banks are gentle, and steep rocky abutments are there on the left bank. The valley is not so wide, so the spillways are accommodated in the valley itself. The thickness of the overburden is high and it has heterogeneous adverse geology at the right abutment. The total height of the NVC's dam is 130 meters. The dam top at elevation 1205 meters and the bottommost foundation level at elevation 1075 meters. The FRL is at 1202 meters. This is the section of non-overflow block of the envisaged dam, and the total height is 130 meters, and it was decided to construct the lower portion of the dam below 1140 meters by RCC method. Above elevation of 1140, CVC method has to be adopted. There were certain site developments. During the excavation of the right blocks, a major slides in the hills on the right side occurred. The geological investigations revealed 2 deep-seated shear zones and several stabilization measures in terms of the grouting, micropiles, cable anchors were carried out. 2 rightmost dam blocks, as shown here. These 2 blocks rest on the weaker rock mass, and so foundation improvement was carried out by casting 2-meter dia board reinforced concrete piles that are rock supported. When the further excavation after the stabilization were underway, a local slide at the dam downstream of the dam axis occurred. This slided mass was stabilized and the benching down in both the banks continued. The left bank excavation has almost reached to the bottom levels and the stabilized local slide was offloaded. The offloading started. During offloading of this slide, the slide gets reactivated. This slide gets reactivated and it covered the right blocks partially, on which the right dam blocks had to be constructed. So subsequently, excavation and stabilization of this reactivated slide was designed so as to start the concreting in the dam blocks. RCC characteristics and the constraints. Originally, when the complete dam was CVC type, no issues related to materials were there. But when the lower half was revised to RCC, then the availability of quality fly ash, that is pozzolana, was looked into. The cementitious material range for RCC mix is between 200 to 230 kg per cubic meter, which requires a large volume of cement as well as fly ash for carrying out the 65 meter of concreting by RCC. The fly ash that would be used for the RCC should meet the physical as well as the chemical quality requirements as per the standards. So 4 or 5 fly ash sources were identified, but the local sources had insufficient quantity. And so a cross-country source was identified which has the required quantity. And also the preliminary test results were carried out that were meeting the quality requirements. But that thermal power plant was 750 kilometers far from the site. So from the dam site to the source of the fly ash, when the fly ash will be transported, it could lead to high transportation cost as well as the handling cost. This table shows the properties of the RCC mix, and one of the properties of the mix is the direct tensile strength of the concrete. Attainment of the desired tensile strength of 1.5 MPa at lift joints was crucial, keeping in view that only one RCC mix will be used for concreting. When a FEM 2D analysis was carried out, it shows that the tensile strength requirement for the upstream and the downstream phases of the blocks, it required 1.5 MPa at 365 days and 0.7 MPa at 180 days in the hearting portion of the dam. This indicates that two different tensile strengths requirement for two concreting mixes. One would be higher. One would be of the higher grade than M50. CVC dams use aggregate size of 40 mm mix M25 on upstream and downstream faces, having a thickness of 2 to 5 meters. The hearting of the dam is being done by aggregate size of 150 mm and M55 grade concrete, but with RCC, the thickness along slopes had gone to 20 to 28 meters. The quantity of cement and aggregates has to be revised, which involves contractual issues, placement rates, and placement methods. When the entire dam was of CVC type, the concreting by cable car system was adopted, and the average placement rate of CVC was comparable to RCC if the cable car system is adopted. But in between, the already cable cars that were being installed became non-operational because of the massive slide that occurs on the right bank. If any other system is adopted, pouring rate of RCC should be more than that of CVC if time advantage is to be gained. So contractual issues could be there. Now, constraints for dam construction by RCC. The RCC placement could not be started due to the existing site conditions. The one reason for this was the temporary unavailability of the access to the dam pit due to the slided mass. A local slide had occurred here, and the only haul road that was there to reach the dam pit was filled with by the slided mass. So there was temporary unavailability of the access. Secondly, no start of activity in right dam blocks could be started until this reactivated slide mass that were there on the block. So the mass, the sliding mass had to be removed for the concreting. Also, blocks, the diameter pile and the pile raft has to be tested, and the pile raft goes till elevation of 1110 meters. So, if the construction of the raft starts, then continuity of the RCC placement at this level could be hampered. Concreting of the left block can be taken to elevation of 1150. Then after, for abutment to abutment concrete crawlers, all right bank activity should be over. The right bank conditions were not favorable because there was slided mass, there were pile cap, casting, there were the issues of also left dam blocks 2 meters flat is to provide the start of the so RCC started when consolidation routings or consolidation routing activities are over. Therefore, decision of the RCC was taken for two considerations. One was the time, the second one was cost neutrality. The RCC placement is comparable to CVC, low time advantage, cost implication in terms of revised concrete needs, its quantities, transport cost, etc. are likely to escalate the prices. Moreover, the existing site pile cap constructions on the right bank path, unavailability of security front throughout the dam, etc. are unsuitable for continuous RCC dam construction timetable. The time advantage by RCC construction is achieved due to fast placement rates and continuous rolling up site. When the site conditions are unfavorable, continuous rolling up placement rates are comparable to CVC. Time advantage gets minimal or loss. The lower part of the Punasanchi dam was revised to RCC to take time advantage and in terms of time. However, the conditions that emerged at dam site were not in favor of continuous how the dam is. RCC concept in the present dam case, that is Punasanchi 1 dam in Bhutan, has not been cost effective and time saving. Had RCC method been conceptualized during tender stage, the uncertainties involved could be minimized and overall planning for dam construction could have done in a better way. Thank you.
Hello.
Hello. Hello.
Hello. Yes, sir.
Uh,
Sir, this session is, I think, finished.
okay, now just wait for a minute.
Okay.
We are thankful to Icold President, Mr. Michael Roser, Dr. Quentin Shah, and his team for making a very extensive and detailed presentation for execution of RCC project from concept to commissioning, be it the planning, design, and the material, as well as quality control. It will be a good exercise and particularly be very useful for the Indian participants, because we in India are planning to have one of the major project, Diwang, of 282-meter height. We certainly look forward to your support for future also. Thank you very much, sir. Hello.
Thank you. Thank you.
Thank you all.
सब